Hi everyone, welcome to goclasses. In this lecture, we will discuss GATE CS All India Mock Test 2 detailed solutions. So this is All India Mock Test 2 detailed solutions part 3. The previous part I will provide you the link in the description. You can watch it from there. So let's start the detailed discussion of AIMT 2 questions for GATE CS 2026 aspirants. First, let me share with you that more than 4,000 students attempted Go classes All India Mock Test 2 for GATE CSE 2026. This test was attempted by more than 4,000 students live. So these are the number of live participants. And I think this is a very good number, very huge number. So I hope all of you loved this test. And I want to thank each and every one of you for your trust in Go classes, for your trust in Go classes mock test, for your trust in Go classes quality and in Go classes AIMTs. So you can see for GATE CS 2026 aspirants, Go classes has so far conducted All India Mock Test 1, All India Mock Test 2, and in these AIMTs, you can see the number of live participants. That is, you can see in AIMT 1, it was more than 3,700, and you can see in AIMT 2, it is more than 4,000. So thank you all. Now let me share with you that the upcoming AIMTs, you can see for GATE CS 2026 aspirants, the upcoming AIMTs, you can see AIMT 3 that will be conducted on Sunday, 4th January. You can see every Sunday, so it is very easy to remember this schedule. You can see every Sunday we have GATE CS All India mock test. Okay, every Sunday. And let me share with you the GATE DA All India mock test schedule. So for GATE DA aspirants, so far we have conducted GATE DA All India mock test 1. This has already been conducted. Now, the upcoming GATE DA AIMTs, you can see AIMT 2, 3, 4, 5. These will be conducted on Saturday. So it is very easy to remember this schedule also. Okay. So every Saturday, GATE DA All India mock test, and every Sunday, GATE CS All India mock test. Now, we will discuss the detailed solutions of GATE CS All India Mock Test 2. So, this is part 3. Let me share with you where you can find part 1 and part 2. So, you can see on YouTube, you can search Go Classes AIMT. This playlist will come. You can see this playlist, Go Classes AIMTs All India Mock Test. This playlist will come. When you click on this playlist, then inside this playlist, you can find, you can see AIMT2 solutions part 1, AIMT2 solutions part 2. Okay, so this was part 2, this was part 1. So these you can find in this playlist. Okay, very simple. Now let's start the discussion of AIMT2 for GATE CS detailed solutions part 3. Let's solve this question from propositional logic, discrete mathematics based on logical arguments. So the question is saying that select the valid argument or arguments. So this is a MSQ question. Multiple options can be correct, where S1, S2 indicate the premises and S is the conclusion. In every option, one argument is given to you, and the question is asking you select all the valid arguments. You can see that in every option we have premises S1, S2, and the conclusion S. And we need to figure out whether this argument is valid or not. So to solve this question, there are multiple ways. First, we will see the logical way to solve this question, or I can say the intuitive way to solve this question, that we will see first. Then we will see a general way to solve this type of question. Okay. So first, let's see the logical way to solve this question. So let me share with you the concept behind this question, or I can say the logical way to solve this question. Let's discuss. So I can say the logical way to solve, intuitive way to solve this question. What is that? So let me share with you the concept. Remember, whenever it is given that P implies Q is true, means in the question, if it is already given to you that this entire statement, this P implies Q, this is true. If this is given to you, okay, this entire thing is given to you that P implies Q is true, then what it means? It means that either P will be false or Q will be true. Remember, if P implies Q is true, then what are the possibilities for P comma Q? What is the truth value combination possible for P comma Q? So let's see what are the possible combinations for P comma Q. P Q. What are the possible combinations? You can see P can be true, Q can be true, because we are already saying that P implies Q is true. Means whenever P will be true, Q must be true. It can never happen that P is true and Q is false. It can never happen because already it is given to you that P implies Q. This whole statement P implies Q. This is actually true. Okay. So what are the possible combinations? The possible combinations of truth values for P comma Q, that will be TT or FT or FF. Okay. Notice one thing, that this TF, this is not possible. Okay. Because already it is given that P implies Q is true. So you can see if you take P true, Q false, then P implies Q will become false. But it is given that P implies Q is already true. So it means that this P true, Q false, this combination is actually not possible. Okay. So here I can say that these are the possible combinations. These three combinations are possible combinations. Possible combinations. You can notice from these possible combinations that when it is given that P implies Q is true, then you can notice that either P will be false or Q will be true. Okay, here this combination, this is FF. Okay, so you can see TT, FT, FF. These are the possible combinations. So you can see when it is given that P implies Q is true, then either P will be false or Q will be true. I can also say that if P is false, then definitely P implies Q will be true. I can also say that if Q is true, then definitely P implies Q will be true. Okay, so very simple. These are the possible combinations. Now, let me ask you one thing. With this statement, if some more information is given to you, means I also give you, also given, also given, what is given to you? It's also given that P is true. Okay, let's assume this information is also given, means already it is given that P implies Q is true. So from this information, from this given information, we can find out that these are the possible combinations of truth values for P comma Q. Okay, let's call it given information 1. Now, also this information is given to you that P is true. Now, what are the deductions that we can make? What are the conclusions that we can make? What we can deduce from this information, also this information. Okay, so two informations are given to us. Now, tell me. So you can see it is given that P is true. Then what are the deductions that we can make? You can see if P implies Q is already true, also it is given that P is true, then definitely this deduction we can make that Q is true. Okay, because you can see from this information that P implies Q is true, from this information we can say that these are the possible truth value combinations for P comma Q. Okay, now if it is also given to you that P is true, okay, just look at the possible combinations of truth values. So here you can see if it is given to you that P is true, if I say that P is true, then definitely Q will be true. Okay, yes or no? So this is the deduction we can make, that Q definitely will be true. Okay, very simple. Now, if instead of this, let's assume this is given to you that P is false. Okay, means this information and this information are given to you. Okay, now what are the deductions that we can make? So very simple. From this information that P implies Q is true, we can deduce that these are the possible input. These are the possible truth value combinations for P comma Q. Okay. Now, if I also tell you that P is false, I also tell you P is false. Okay, you can see in these possible truth value combinations, if I say that P is false, then what can you say about Q? We cannot say anything about Q because Q can be true, Q can be false. So basically, I can say that we cannot say anything about Q. If I say that Q is true, that also will be a false deduction. If I say Q is false, that also will be false deduction. Q can be anything. I cannot say that Q is true. I cannot say Q is false because Q can be either true or Q can be false. So we cannot say anything about Q. Okay, yes or no? So basically, nothing about Q we can say. Nothing about Q. Okay, we cannot say anything about Q. Very simple. Now, let's assume that I give you this information that Q is true. Okay, I give you this information that Q is true. So now remember, this information and this information, these two information are given to you. So tell me, what are the deductions that we can make? You can see from this information that P implies Q is true, we can find out that these are the possible truth value combinations. Now, I also tell you that Q is true. I also tell you Q is true. Then what can you say about P? I cannot say anything about P because P can be true, P can be false. So basically, there is nothing we can say about P. If I say P is true from this information and this information, if I say that P is true, that will be false deduction. If I say P is false, that will be false deduction. So basically, nothing about P we can say yes or no. So here I can say that again, here I can say that about nothing about P we can say here. Very simple. Now, let me ask you, if I tell you that Q is false, means this information and this information, these two information are given to you, then what can we say about P? So you can see from this information that P implies Q is true, we can say that these are the possible truth value combinations. Now, I tell you that Q is false. On top of this information, I tell you that Q is false. Then what can you say about P? Definitely P will be false. Yes or no? So here I can say that P will be false. This deduction I can make from this and this information that P will be false. I hope you understood. So this is the logical way to solve this question. Now we can very easily solve this question. So let's see all the arguments that are given to you. Let's write them in the argument form. Right now, these are the English statements. You can see what we will do. We will convert them to propositional logic expressions. Okay. So here you can see these are the statements, or I can say these are the propositions that the horse is tired. The horse is tired. Let me write it, let me denote it by the variable, propositional variable h. Okay, it will lose the race. Let me denote by the propositional variable l. Okay, now you can see what this s1, what is s1? S1 is that if horse is tired, then it will lose the race, means if h, then l. Okay, this is s1. What is s2? Horse was rested, so this is negation of h. Okay, you can see the horse is tired, this we are representing by propositional variable h. So horse was rested, this will be negation of h. Now some students, I have seen some students are thinking, sir, how do we know that the negation of horse is tired will be horse was rested? So I will say it is common sense. Also, you can see the context of the question. This question is not about English language. This question is about logical arguments. This question is about propositional logic. Okay, propositions. So here you have to understand the context of the question. In the context of the question, of course, it's quite common sense that the horse is tired. If this we represent by h, then the horse was rested. This will be negation of h. Okay, so sometimes you have to understand the context of the question. Not everything will be given to you on the silver platter, right? Okay, sometimes you have to understand the context of the question, context of the problem, context of the subject. Sometimes you have to read question maker's mind also. In gate exam also sometimes it happens that sometimes you have to read the question maker's mind. Every year in the gate exam, out of 65 questions, there are 1 2 question which have some kind of ambiguity, which I can say that they are not as well framed as they could be. Okay, so in those questions sometimes you have to read the question maker's mind also. Okay, so anyway, this is not something that you cannot do in this question. I can say in this question it's very common sense, or I can say it's very clear that if I represent the horse is tired with propositional variable h, then the horse was rested, this will be negation h. Okay, next you can see the conclusion, because this is the conclusion. The conclusion is that horse won the race, so that will be negation of l. Okay, so very simple. Here I can say that s2 is negation of h, and what is s? This is negation of l. Okay, now this s is the conclusion. So now notice one thing here. This information is given to you, and we need to check, can we deduce this information or not? Remember, this is what the argument means. In the propositional logic, what is an argument? Argument is basically a sequence of statements where we have some premises, and we have conclusion. Okay, so you can see that these are the premises and this is the conclusion. When can I say argument is valid? We can say argument is valid whenever the premises are true, then the conclusion must be true. Okay, or I can say that from these premises, can I deduce this information? Okay, yes or no? So this is what the argument means, or I can say this is what the this is what the valid argument means. Valid argument, when can I say any argument is valid? I can say argument is valid whenever the premises are true, then the conclusion is true, or I can say that from the premises we can deduce that the conclusion will be true. Okay, this deduction we can make from the premises. Very simple. So here you can see these two information are given to us, that H implies L. Okay, and negation H. What this negation H means? That H is false. So can we say L is false? Okay, negation H, it means H is false. Negation L, it means L is false, and already it is given to you. Now you compare with this situation here. You can see P implies Q is given to you true. You can see H implies L. This is given to you true. Okay, because these are the premises. You assume the premises are true. Now you find out, can we deduce the conclusion or not from the premises? Can we derive the conclusion or not? Okay, very simple. So remember here, you can see P implies Q is true. This is already given to you. H implies L is true. Now you can see also it is given to you that H is false. Okay, this LHS, this H is false. So basically these two information are given to you. Now notice here, P implies Q is true. This information is given to you. And you can see this P, this is false. This information is given to you. This information, these two information are given to you. So tell me, can we deduce anything about Q? No, we cannot deduce anything about Q. Yes or no? Because you can see when P is false, then remember Q can be true, Q can be false. So if you say Q is true, that also will be false deduction. If you say Q is false, that also will be false deduction. Okay, so here I can say that from this information, from this given information, remember, we cannot say anything about L. If you say L is false, that will be false deduction. If you say L is true, that will be false deduction. So here, if the conclusion is negation L, this is also invalid argument. And if the conclusion, if that is L, if the conclusion, let's assume instead of this negation L, if the conclusion is L, that also will be false deduction. Okay, you can see in which option the conclusion is L. So you can see here in one of the option, maybe you will see that conclusion is L. Yes, look at this option D. Look at this option D. In this option D, what we have, you can see what is S1. S1 is if horse is tired, that we are representing by H. Okay, yes or no? So you can see if horse is tired, then it will lose the race. This is we are representing by L. What is S2? S2 is the horse was rested, so that is negation H, means H is false. Okay, and what is the conclusion? S is the conclusion. You can see S is the conclusion. The conclusion is horse lost the race. Okay, means L. So you can notice one thing, that from this information, also you can see this and this, they are the same information. Okay, so remember, from this information, from this and this, of course they are same. So you can see the premises are basically same in option A, option D. And this is what I'm telling you, that if these two information are given to you, that H implies L and H is false, okay, you can see, then from here, what can we say about L? Okay, what can we say about L? So you can see here basically P is H and Q is basically L. The question is saying that H implies L is true. Okay, also the question is saying option A, option D. I'm talking about option A comma D. So you can see option A comma D, they are also saying that H is false. Negation H means H is false. So you can see they are also saying that H means P is false. Okay, so remember, basically this information and this information is given to us. Now what can we say about Q? Nothing can be said about Q. If you say Q is true, okay, you can see here P is false, this is given to you, means H is false, this is given to you. So if you say that Q is true, that will be false deduction. If you say Q is false, that will be false deduction. So finally I can say that if you say conclusion is negation L, means the conclusion is L is false. Or if you say conclusion is L is true, then both these conclusions are false conclusions, or I can say these are false deductions. If these are false deductions, then I can say that this argument and this argument, they are invalid argument. I hope you understood this point. Okay, so the question is asking valid argument. Actually, these are invalid argument. I can say that this entire argument, this is invalid argument, or I can say that this is false deduction. Okay, I can say that this is invalid argument. I hope you understood. Now let's see option B comma C. What about option B? Option B is saying that what is S1? If the horse is tired, it will lose the race. Already, this horse is tired. This proposition, this statement we are representing by propositional variable H, and it will lose the race. This we are representing by propositional variable L. Okay, so what is S? This is basically H implies L, because if H then L, so that is H implies L. What is S2? S2 is the horse won the race. So that is negation of L. Okay. And you can see what the conclusion. The conclusion is horse was rested. This is negation of H. Okay. Let's see option C also. What will be the argument form for option C? So you can see that the horse, if the horse is tired, it will lose the race. So in this option C also, you can notice what is S1. That is H implies L. Okay. What is S2? That is the horse lost the race. Means that is negation L. The conclusion, that is the horse was tired. The horse was tired means the horse lost the race. That is basically L. Okay, that is not negation of L. That is basically L. Okay, the horse lost the race. That is L. Okay, because you can see the horse is losing the race. Basically, this we are representing by L. So the horse lost the race. That is basically L. And you can see the horse was tired. This is basically H. Okay, so this is option C. Now let's see option B, option C. These arguments, are they valid or not? Okay, let's see what this argument is saying. This argument is saying that if H then L is false, then can we deduce that H will be false? Okay, notice one thing here. This is given to you true because these are the premises. This is the conclusion, and we assume that premises are true. Now, can we deduce? Can we make a deduction that this conclusion will be true? Okay, so you can see here that H implies L. This is given to you true. Also, L is false because negation L. This means L is false. Means this L is false. So can we say that this H will be false? Because the conclusion is that H is false. You can see negation H means H is false. Okay. So let's come back to this logical way of thinking. You can see here, this is given to you that P implies Q is true. Also, it is given that Q is false. So what can you say about this P? You can say that P will be false. Okay. So yes, that is the same thing given to you in option B. In option B, we are saying that H implies L is true. Also, L is false. Then definitely H will be false. Because remember, if L is false, then H cannot be true. If H is true, then this whole thing will be false. Yes or no? Because remember, it is already given to you in the premises. In the premises, it is given to you that L is false. Negation L means L is false. So if L is false, then can H be true? If H is true, L is false, then the whole thing will be false. But we assume that premises are true, and then we find out can we derive this conclusion or not. Okay, so you can see here, if L is false, then definitely H will be false, and that is the conclusion. So yes, this is a correct deduction, or I can say this is a valid argument. Okay, yes or no? So I can say this is a valid deduction, valid argument, or I can say this is a correct deduction. Okay, so you can see valid argument. Very simple. Now let's see option C. Option C is saying H implies L, and this L is true. Then can I say H will be true? Okay, let's come back to logical way of thinking. It is given to you P implies Q is true. Also, it is given to you that Q is true. Then what can we say about P? Nothing can be said about P. So if you say P is true, that also will be false deduction. If you say P is false, that also will be false deduction. Okay, so here you can see that this option C, this is basically invalid argument. Okay, this is basically invalid argument. So you can see here, this will be invalid Invalid argument. Okay, I hope you understood. Remember, if you say in the conclusion, if you say H or if you say negation H, both are actually invalid argument. Okay, so here conclusion H, this is also invalid argument. Instead of this, if I make conclusion negation H, that also will be invalid argument. So here let me make a variation here. Means a variation means if I give you like this, that okay, this H implies L, then L, and here if I say that okay, negation H, then remember this is also invalid argument. This argument, this is also invalid. Okay, I hope you understood the logical way of solving this question. This is how you can solve this type of questions in a logical way in the exam. Now, there is another way to solve this question. The same question we can solve in a general way also. What is the general way? Let me share with you. You can see. First, let's see the definition of valid argument. You can see. When can I say argument is valid? An argument is valid. First of all, what is argument? Argument is a sequence of statements where we have premises, also we have conclusion. Okay, so you can see this is argument. Argument means sequence of statements where we have premises, we have conclusion. Okay, then what is the definition of valid argument? Valid argument means argument is valid if whenever all the premises are true, then the conclusion must be true. Okay, if all the premises are true, whenever all the premises are true, then definitely conclusion must be true. Then we will say that argument is valid. Okay, very simple. Now let's see the definition of invalid argument. When can I say that argument is invalid? Argument is invalid if it is possible to make all the premises true and the conclusion false simultaneously. Okay, very simple point. When can I say argument is invalid? Argument is invalid if it is possible to make, there is some possibility that we can make all the premises true and the conclusion false simultaneously. If we can do this, if this is possible to do, that we are making all the premises true and the conclusion false, if it is possible to do simultaneously, then definitely I can say that argument is invalid. Okay, now you can see there is another way to say that argument is valid. What is that? Argument is valid if it is never possible to make all the premises true and the conclusion false simultaneously. Okay, means if you can see that it is never possible, it is never possible that simultaneously you can make all the premises true and the conclusion false. If it is never possible, then definitely I can say that argument is valid. I hope you understood. Now let's see the method, the general method to check whether a given argument is valid or not. So you can see it is very easy method. First you make the conclusion false. Now you try your best, you try to make all the premises true. If it is possible, what is possible? If it is possible that after making the conclusion false, if you can make all the premises true, if it is possible, then argument will be invalid. And if it is never possible, then argument will be valid. Okay, so this method, this simple method you can apply on this question. This is a general method. So let's solve and let's see what will be the answer. So first let's see for option A. In option A, these are the English statements. Let's convert them to propositional logic format, or I can say in the argument form. Okay, so you can see what is S1. S1 is basically H implies L. And what is S2? S2 is negation H. And what is conclusion? You can see conclusion, that is the horse won the race, that means negation L. Okay, now let's see whether this argument is valid or not. So what we will do, the method I already told you, you make the conclusion false. Okay, let's make this conclusion false. So let's make it false. This conclusion I am making false. What it means? Negation L is false. It means L will be true. Yes or no? It means L will be true. Now what you do? You try your best to make all the premises true. If it is possible, then we will say argument is invalid. If it is not possible, then argument is valid. Very simple. So what we do? We try to make all the premises true. You can see already L is true. Already this L is true. So this entire thing is already true. Okay, you can see. Anything implies true, that will be true. So here I can say that S1 has become true already. Okay. So remember, I have freedom. I can make S true, I can make S false, whatever I do. Already L is true. So you can see anything implies true, that will be true. So already this S1 has already become true. Now, can I make S2 true? Yes, I can make S2 true because I can make S false. If I make S false, then I can make S2 true also. Yes or no? So you can see I make H true also. Sorry, if I make H false, if I make H false, then negation H will be true. So you can see, now you can notice after making the conclusion false, I have made I have made both the premises true. So you can see I have created a situation where all the premises are true, but the conclusion is false simultaneously. It is happening simultaneously that all the premises are true, but the conclusion is false. So definitely in this situation, I can say that argument is invalid. Okay, yes or no? So definitely I can say that this argument is invalid. Okay, very simple. I hope you understood this. Now let's see option B. In option B, first you write the argument form, means you convert these English statements to a propositional logic format, to propositional logic expressions. So you can see, if horse is tired, then it will lose the race. Horse is tired implies it will lose the race. Okay, because if H, then L. Okay, now you can see what is H2, another premise, that is the horse won the race. That means negation L. Okay, the horse won the race. What is the conclusion? The conclusion is the horse was rested. Means the horse was not tired, or I can say the horse was rested. So negation H. Okay. Now here you can see. Let's see whether this argument is valid or not. So the general method I already told you. What you do? You make the conclusion false. Okay, let's make it false. So if you are making the conclusion false, negation H false, it means that H will be true. Okay, already H is true. Now you try to make all the premises true. Okay, but remember, already this H is already true. So if I want to make this S1, this premise 1, if I want to make this premise 1 true, then already this LHS is true, LHS of implication is true, then definitely this RHS also must be true. Yes or no? So remember, I have to make it true so that the first premise can become true. Okay, now notice, can I make this premise S2 also true? No, I cannot do that, because already you can see that to make the premise 1 true, already this L is true. L has to be true. So now you can see that this S2 will be false. Yes or no? So you can see this S2 will be false. I cannot make this S2 true. So you can notice, after making conclusion false, it is never possible that I can make all the premises true. I cannot create a situation where all the premises are true, but the conclusion is false simultaneously. So that is the reason I can say this argument is actually valid argument. Okay, very simple. Now let's see the next option. The next argument. So let's write the argument form. If the horse is tired, then it will lose the race. What is another premise? That is the horse lost the race. That is L. And the conclusion, that is the horse was tired. Okay, that is basically H. The horse was tired. So this we are representing by H. Very simple. Now let's see whether this argument is valid or not. So to check that, what we will do? To check whether a given argument is valid or not, what we will do? We will make the conclusion false. So to make the conclusion false, this H will be false. Now we will try our best to make all the premises true. Okay, so you can see, if I want to make S2 true, then what I need to do? I need to make L true. Yes or no? Then you can see S2 has become true. But now I also want to make S1 true. So can I make S1 true? You can see already L is already true. H is already false. Okay, so false implies true. That is true. So you can notice that after making conclusion false, I have made all the premises true. I have created a situation where all the premises are true, but the conclusion is false, and this is happening simultaneously. So you can see that this argument, this is also invalid. Okay, very simple. Now let's see the last option. The last argument, is it valid or not? So you can see option D in the argument form, what it will be. The premises are, if the horse is tired, then it will lose the race. Another premise, that is the horse was rested. Horse was rested. What it means? It means negation H. And you can see what is option, what is the conclusion? The conclusion is the horse lost the race. Okay, now let's see here to check whether this given argument form, it is valid or not. We will make the conclusion false. Let's make it false. Now we will try our best to make all the premises true. Okay, you can see already this L is already false. So how can I make S1 true? To make S1 true, already this RHS of implication is false. So to make this implication true, I must make H false. Okay, then you can see this S1 will become true. Now, let me also make this S2 true. Can I make S2 true? You can see H is already false. So negation of false, that will be true. Yes. So S2 has also become true. So remember, after making conclusion false, I can make all the premises true. Then I can say this argument, this is also invalid argument. Okay. This is also invalid argument because I created a situation where simultaneously the conclusion is false and the premises are all true. Okay, so that is the reason I can say that this argument is invalid. Remember, argument is valid if and only if whenever the premises are true, whenever in any situation if you can make premises true, then in all those situations, remember, the conclusion must be true. Okay, whenever the premises are true, the conclusion must be true. It should not happen that you can make premises true, all the premises true, but the conclusion is false. If it is possible, if you can do that, okay, all the premises are true but still the conclusion is false, if you can do it, if you can do it simultaneously, then definitely I can say that argument is invalid. Okay, so that's it. This is the complete analysis for this question. This is actually a very easy question, but because we solved this question by two methods, one logical way, another general way, so that is the reason it took time. Also because I am explaining to you, that is the reason it took time. But actually this is a very standard question in the propositional logic, and this won't take, I think, more than 1 minute. Okay, so if you understood the logical way, if you understood the general way, both methods, both the ways are actually very important. Okay, you might be thinking the logical way was nice, very good, but sometimes the general way is also very good. Okay, when the argument is complicated, if they give you some complicated argument, many premises and then conclusion, then in this situation you can apply the general way. So remember, both the methods you need to understand, both are nice, and you can apply depending on the question, you can apply any of these methods in the exam. Okay, I hope you understood this complete analysis. Let's solve this question from DBMS SQL. This is a very nice question. Let's solve it. The question is saying that two queries are equivalent on a database instance if they produce the same result when evaluated over that instance. So this is the definition given to you for equivalence over instance. What is instance? This is basically a particular snapshot of the table. Okay, a particular data with a particular data. So you can see if an instance is given to you, and on that instance, if two queries are producing the same result, then we will say that these two queries are equivalent on this particular instance. But when we can say that two queries are always equivalent, so that is also given to you here. You can see two queries are equivalent. When can I say two queries are always equivalent? Or I can say, when can I say two queries are equivalent? Two queries, two SQL queries are equivalent when they are equivalent on every possible instance. Okay, very simple. So let's read this question. Two queries are equivalent on a database instance if they produce the same result relation they produce when evaluated over that instance. Okay, consider a SQL database with two tables. There are two SQL tables, are a comma b, two attributes, as c, there is only one attribute in this SQL table. You can see, assume null values are not permitted in any attribute. This is given to you that you cannot have null values in any attribute. So basically there is a constraint, that is not null constraint. Okay, a is not null, b is not null, c is not null. Okay, very simple. The question is saying make no other assumption about the data. So basically, other than the null values are not permitted. Other than this, we cannot make any assumption about the data, about the instance, about what data is present in R comma S. Very simple. Now the question is saying below are the pairs of queries. You can see some pairs of queries are given to you. In every option, a pair of queries is given to you. You can see query 1, query 2, query 1, query 2. So in every option, you can see that pairs of queries are given to you. In which of the following options the two queries are equivalent on every possible instance? Means, in which of the following options can I say that the queries are equivalent? Or I can say the queries are always equivalent, or I can say queries are equivalent. Okay. So the question is asking select all correct options, means this is a MSQ question. So multiple options can be correct. Okay. So I hope you understood the question, what the question is asking. Now let me tell you that to solve this question, actually there are multiple methods. So we will see both the methods, or I can say multiple methods to solve this question. We will do the complete analysis of this question. First, we will see how to solve this question by taking an example. And then we will see how to solve this question by the logical interpretation of queries. Okay. So both the methods we will see how you can solve this question by taking example, means by taking instance, and how can you solve this question without taking instance but actually finding the logical interpretation of the queries. Okay, so both the methods we are going to see now. So first we will see the method number 1, that is we will take instance and then we will see whether the queries are equivalent or not. Okay, very simple. So you can see this method number 1, given an SQL query, to understand the behavior or output, taking a generic instance can sometimes help. Let me tell you one thing. If you take one example, let's zoom on this instance. If you find out that query 1 and query 2 they are giving different result, then immediately you can say that query 1, query 2 are not equivalent. Okay, because you took one particular instance. Okay, some data you took, some particular instance you took. On this instance, when you are running this q1, q2, these queries, then let's assume they are giving different results. Okay, the output result relation that is different. Then you can immediately say that these queries are actually not equivalent. But remember, if I take one particular example, one particular instance, and on this instance, let's assume that Q1, Q2, they are giving the correct, or I can say they are giving the same result relation. The output is basically same for this particular instance. For this Q1 and Q2 query, the output is same. Then remember one thing, we actually cannot say that these queries are equivalent, because two queries will be equivalent if they produce the same result on every instance. But so far we only checked for one instance. Maybe there is another instance for which they will produce different result. Okay, so remember this method number 1, this is good for elimination. This is actually not good for proving that two queries are equivalent. But this method number 1, this will give you the idea about the behavior of the query. Okay, so this method number 1 is also a very good method because it will tell you about the behavior of the query. And one more thing, if you select a generic instance, okay, you can see here I am using the word generic instance, means if you select an instance which covers all the possibilities, okay, all the corners, all the possibilities, if your instance covers, then definitely I can say almost 99% times you can get your answer. If you are taking a generic instance according to the given queries, okay, you will see, okay, as when we do the analysis, you will see that according to the given queries, I will take generic instance and then I will eliminate the options. On this generic instance, if two queries are giving different output, then definitely I can say those two queries are not equivalent. But on this generic instance, if two queries are giving same output, then actually it is not a proof that those queries are equivalent. It is not a proof. We cannot say for guarantee, we cannot say that those are actually equivalent queries. Okay, because maybe there is some other instance where they will produce different result. But I can say that if you are taking a generic instance, then most probably you will arrive at the correct answer. This is what I'm saying. Okay, so let's see method number 1. Let's see this. Given SQL query, to understand its behavior, to understand its output, taking a generic instance can sometimes help. Okay, so what you do, you take a simple generic instance which covers all the possibilities, all the corner cases, all the possibilities it covers, is specific to the given queries. Okay, so look at the given queries, look at the given SQL query, and then according to the given SQL query, you take a generic, simple generic instance you take, which covers all the possibilities. Then this method will most probably, or I can say almost always, this will give you the correct answer. Okay, very simple. So this is a very useful method. Of course, we will see the method 2 also, where we will, without taking the instance, without taking example, we will basically find the logical interpretation of the query, and then we will see whether they are equivalent or not. But first, let's focus on this method number 1. So now we need to take generic instance according to the given SQL query. So here, let me tell you one thing about SQL. Basically, some revision of SQL let's do, because this is very important. Many students have misconception here, because many students they think that the database table cannot have duplicate rows. Okay, yes or no? Many students they think that the database table cannot have duplicate tuples. For example, if you have a relation R A comma B, then many students they think that this type of duplicate tuples are not allowed. So let me tell you, duplicate tuples are not allowed in the relational algebra. Duplicate tuples are not allowed in the relational model, which is a theoretical model. But SQL is not a theoretical query language, it is a commercial query language. Okay, and SQL allows duplicate tuples by default. Okay, so let me tell you about this point here. You can see that SQL treats table, or I can say the database relation, as a multi-set, as a bag, not as a set. Remember the definition of set. The definition of set says that the duplicates are not allowed. Okay, yes or no? What is a set? Set is basically unordered collection of distinct elements. That is the definition of set. But what is a multi-set? Multi-set is basically unordered collection of elements. They can be same element, distinct element. Okay, basically repetition is also allowed in the multi-set. So remember one thing, that SQL treats the table, the database table or the database relation as a multi-set. It is also called bag of tuples. Means by default, the duplicate tuples are actually allowed in SQL. Okay, so you can read this, that SQL by default allows the same tuple to appear more than once, unless some primary key or some candidate key or some key constant is defined or given. So in your question, if some primary key is given to you, if it is given that okay, this is the primary key in this relation R, in the relation R, let's assume this A is the primary key, then you cannot take duplicate tuples. Okay, but remember, by default, if no primary key is given to you, no primary key information is given to you, no candidate key information is given to you, no key constant is given to you, if this information is not defined or not given, then remember by default SQL allows same tuple to appear more than once. Okay, because SQL table is basically multi-set, or I can say bag of tuples. Okay, but remember, if you compare this with the relational algebra is a theoretical language. It is a theoretical query language. Relational model, that is a theoretical model. In those models, in the relational model, also in the relational algebra, what we have set of tuples. We cannot have duplicate rows in our table. Okay, so here you can compare SQL with the relational algebra. So you can see, what is a set? You already know set means no duplicates. Set is unordered collection of distinct elements. So in a set, duplicates are not allowed. And you can see relational model and the relational algebra, they use the set semantics. Means in the relational model and in the relational algebra, the inputs are also set of tuples and the output is also set of tuples. Means the inputs cannot have duplicate tuples and the output also cannot have duplicate tuples. But remember, SQL uses bag semantics. SQL uses bag semantics by default. What it means? It means that in SQL, the input table, the input also can have duplicate tuples and the output also can have duplicate tuples. Okay, so very simple. You can see bag. Bag is basically multi-set. Another name for bag, that is multi-set. Duplicates are allowed. Unordered collection of elements, but actually duplicate elements are actually allowed. And number of duplicate also, that is also matter. Okay, means if you have A 3 times, if you have A 2 times, then these are different in a bag, in a multi-set. Okay, because you can see that here you have 3 times A, here you have 2 times A. So these are actually different things. Okay, so you can see that in a multi-set, in a bag, the number of duplicates is also significant, or I can say that number of duplicates also matter. And SQL uses the bag semantics by default. Okay, so in SQL, remember, the input tables also can have duplicate tuples, and the output table also can have duplicate tuples, unless some primary key or key constant is defined. If some primary key or key constant is defined, then of course the table cannot have duplicate tuples. Okay, very simple. So let's solve this question one by one. Each option we are going to check, and the method one we will apply. The method one is basically you select a generic instance according to the given queries. Okay, so let's see each option one by one. First, let's see this option A. So this is option A. Two queries are given to you, query one, query two. Actually, this option A is actually very easy. So let's solve this option A. You can see in this option A, what I will do, I will take a generic instance. Okay, so what I will do, remember R has two attributes A comma B, and S has one attribute C. Okay, so let me take a generic instance according to the given query. You can see what is this query. This is saying select A from R, means from this table you just select this A, this attribute A. Very simple. Query 2, this is saying select A from R comma S. From R comma S means this this conceptually it means R cross S. Okay, R cross S. This is what it conceptual meaning. Okay, conceptual. This is the conceptual meaning. When we write from R comma S, then the conceptual meaning is basically that R cross S you are doing means every tuple of R with every tuple of S. Okay, you are doing the cross product here, means basically you are joining, or I can say that you are combining every tuple of R with every tuple of S. Okay, combining every tuple of R with every tuple of S, this is called cross product. So you can see when we write from R comma S, then conceptually it means R cross S. Okay, now what I will do, I will take a generic instance here. So let's take a generic instance. For example, let me take 1 comma 2. Notice my thought process, what I'm thinking. You can see the question, what this question is saying. The question is actually saying that make no other assumption about the data, means we cannot make any assumption about the data. Also, you can see the question is not saying that R has a primary key. Maybe R has no primary key, maybe S has no primary key. Okay, so remember, R comma S, they can have duplicate tuples, but remember they cannot have null. Already it is given to you that null values are not permitted. Okay, so here what we will do, let's take a generic instance. So I will take one tuple which does not have a duplicate. You can see this 1 comma 2, I will make sure that it does not have duplicate, but I will take another tuple which will have duplicate. Okay, so like this, I think this will be enough for this particular question. I think this instance will be enough because not more information we have here, or I can say not more things we have in this query 1, query 2. According to query 1, query 2, I am taking a instance here. Okay, so you can see that I think this will work. Okay, this will be fine because I have taken one tuple which has single tuple, or I can say that which does not have a duplicate. I have taken this type of tuple also, and I have taken this type of tuple also which has duplicate. Okay, so I think this is the generic instance from these two query point of view. Okay, and in this option C, sorry, in this table S, or I can say in this attribute C also, what I can do, I can take a generic instance, means what I can do something like this. For example, I can take 5 5 6. Okay, so let me do like this. Okay, now you can notice that I've taken a tuple which has duplicate, I've taken a tuple which does not have duplicate. So according to these two queries, I have taken generic instance, I have taken. Okay, now let's see what will be the output of query A. Let's see query A output relation. So what will be query A output relation? Query 1, query 1, you can see. So for query 1, what will be the output relation? You can see in this query 1 we are doing select A from R. Okay, basically we are only considering this table R, and from this table R we need to project this attribute. Only this attribute A we are projecting. In SQL, this select means projection. This is similar to projection, but remember here This is select, this is not select distinct. Okay, so this is similar to projection, but this is similar to projection, but with duplicates not removed, but duplicates kept, not removed. Okay, is this clear? So this is similar to projection, but with the duplicates kept, or I can say duplicates not removed. So here you can see that from this table we are selecting this A. Okay, this attribute A we are projecting. So the output will be basically, output will be 134. Okay, this will be the output. 133. Okay, this will be the output 133. So you can see in the output of query 1 we have three tuples. Okay, in the output of query 1 there are total three tuples. Now let's see query to output. What will be query to output? You can see the query 2 is saying that from R cross S, from R comma S. So conceptually it means R cross S, means every tuple of R we will combine with every tuple of S. Okay, and then we are selecting A. Remember, there is no select distinct here. Here again, duplicates will be kept, duplicates will not be removed. Okay, so here you can see, first of all, in R cross S, how many tuples will be there? Every tuple of R will be combined with every tuple of S. So you can see it will be like this. Okay, then you can notice that it will be like this, and then you can see that it will be like this. So total in this R cross S, total how many tuples will be there? That will be 3 into 3, that will be 9. 9 tuples will be there. And then from this R cross S we are projecting this attribute A. Okay, so you can see the output, what it will be. So let me tell you the output. You can see the query to output relation this will have. You can see, you can notice that this one, it will come three times. Okay, yes or no? So you can see this one will come three times, because this one to this tuple will combine with every tuple of S. So it will be like 1 to 5, 1 to 5, 1 to 6. And then when you select A, then you can see this 1 1 1, it will come three times. Okay, next you can see this 3 will come three times, then this 3 will come three times. Okay, so you can see that this 3 will come three times, and you can see this 3 also will come three times. I hope you understood this point. So did you notice that query 1 output, query 2 output, they are different? Okay, so we can eliminate this option A. Okay, because I can say that query 1, query 2, they are definitely not equivalent. Okay, yes or no? So I can say this option has been eliminated. Query 1, query 2 output, they are different for this particular instance that we have taken. So definitely these two queries are not equivalent. Okay, yes or no? So I hope you understood this. You can notice in the query 1 output we have three tuples. In the query 2 output there are total 9 tuples. Okay, very simple. So one more thing I can ask you, like in this query 2 output, how many times any A value will come? Any A value, I can say any A value will come in this query 2 output, how many times? Okay, so this is a very simple question I'm asking. I'm asking that this query 1 is very simple, right? In this query 1, okay, let's do the interpretation. The logical interpretation also, let's try to understand without taking the instance. You just try to understand what this query 1 is doing. Notice in this query 1 we have basically, in this query 1 we have select A from R. Okay, now notice that we have two tables. R has A comma B and S has C. Okay, so here you can see this query 1 is actually very easy. Here we are saying that from R you are just selecting A, and this is not select distinct. Okay, so you can see we are just selecting A. So here I can ask you that any A value, how many times it will come? Any A value, any particular A value, how many times it will come in the output of query 1? So the answer is as many times as it appears in this original table R. Okay, yes or no? Basically here I can say that the output, you can see the output is RA as it is. Okay, yes or no? Is RA as it is. No duplicates removed. Okay, yes or no? No duplicates removed. No duplicates removed, nothing more added. Okay, no duplicates removed, as it is. As it is. Okay, very simple. So for example, if you have like 1 1 2 2 3 3 3 3, okay, then in this situation basically this output will be as it is. Okay, very simple. I hope you understood. Now let's see query 2. In this query 2, what we are doing, we are selecting A, but from whom? From where? From R comma S. Okay, so this is like R cross S conceptually. So you can see that, notice one thing, how many times any A value will appear in the output of query 2, that will be the cardinality of S multiplied by how many times that value appears in R. Okay, so this is the idea. I hope you understood. So here I can say that any particular A value, any, you can see any particular A value, any particular RA value appears in output of query 2 how many times? How many times? Okay, so what will be the answer? What is going to be the answer? So you can see any particular value, for example this value 1. Okay, so any particular value, okay, or you can take this value 3. So you can see that any particular value, any particular RA value appears in output of query 2 how many times, and what will be the answer? The answer will be how many, how many times that value appears in this RA, okay, multiplied by the cardinality of S. So I can say the size of S multiplied by the number of times that value multiplied by frequency of that frequency of that value. I can say frequency of that value in R. Okay, is this clear? So very simple. I hope you understood this. So anyway, the point is that this query 1 and query 2, they are basically not equivalent. Okay, is this clear? I hope you understood. But tell me, in which situation I can say that, what should I do to make them equivalent? Just a variation. I want to ask you, like, what should I do to make them equivalent? If I want to make them equivalent, then what can I do? Let's see. What can be done to make them equivalent? What can be done to make query 1, query 2 equivalent? Okay, so let's see this. To make them equivalent, what can be done? So let me tell you the solution 1. Okay, what I can say, what you can do, you can restrict the size of S to 1. Okay, means make the cardinality S to 1. Okay, like just force S to have cardinality 1. Okay, is this clear? Let's assume in the question it is given. Let's assume in the question it is given that the cardinality of S is 1. Okay, then definitely I can say that, in if this condition is enforced, if this condition is given, then definitely I can say query 1, query 2 will be equivalent. Okay, very simple. But of course there are more solutions. What are the solution to? The solution to is that, what you can do, you can put distinct. Okay, yes or no? In this query 1 also you can put distinct, select distinct A. Okay, in the query 1 also you can put select distinct A from R. And in this query 2 also, what you can do, you can put select distinct A from R cross R comma S. Okay, so if you do this, then also they are equivalent. Then also they will become equivalent. Okay, I hope you understood this. Very simple. So we have done the complete analysis of option A. We have seen this option A from method 1 point of view, also method 2 point of view, means we have seen the logical interpretation of these queries, query 1, query 2, the logical interpretation we have seen. Also we have seen that they are not equivalent by taking an instance. The instance that I took, that was a generic instance. Okay, I have tried to cover all the possibilities in my instance from the query point of view. Okay, so I hope you understood the analysis of option A. Now let's move on. Now let's see option B. In this option B also we are going to do the same thing, means first we will solve this option B by taking an generic instance from the query point of view. First we will observe the query, and then we will decide in my instance which data I should keep. Very simple. Okay, so here you can see that in this query 1 we are saying select max A from R. Now notice one thing, here max is playing some role. Yes or no? In the A attribute, the maximum value is playing some key role here. So I will try that in my instance also. What I will do in my instance also, I will try to make sure that all the possibilities from the maximum value of A point of view I cover. Okay. So what I'm saying that I want to make a generic instance which will cover all the possibilities, but from the query point of view, the query is telling me which type of instance I should take. Okay, this information is given by the query. Here you can see from the query I am finding that, okay, in my instance, in my generic instance, which type of data I should take to test. Yes or no? So here, of course, the maximum value will play some role here. Okay, so I will consider that I will consider all the possibilities from the maximum value point of view also. Okay, next let's see the query 2. This is saying select A from R, where A is greater than all, select A from R. Okay, so let's take the generic instance here. So here we have this relation R and this relation S. Okay, now what I will do here, you can see that, let me take this type of instance 1 2. Okay, then 3 4 3 4. You can see what I'm doing. I'm doing something like this, that this tuple does not have duplicates, this tuple has duplicates. I'm covering all the possibilities. Okay, also the question is saying the maximum value is playing some key role here. Here basically in this column the maximum value is playing some role here. Okay, so what I can do, for example, let's assume that 4 is maximum value. Let's assume, okay, let's assume 4 is maximum value. So let me take multiple tuples for this maximum value 4. Okay, are you getting my point? So I'm taking this instance, but notice one thing, in this instance I am taking multiple tuples for this maximum value of A in this table R. Okay, this is the maximum value of A in this table R. I am taking multiple tuples. Okay, because I know that this maximum value will play some key role in evaluation, or I can say in the comparison of query 1 comma 2. Okay, yes or no? Of course, what I tell, let me tell you one more thing. Let me tell you, if taking this instance, by taking this instance, if I cannot eliminate option B, then remember what will happen. At least I will get to know the behavior of this option B. At least I will understand the behavior of query 1, query 2. Once I understand the behavior of query 1 and query 2, then I can apply the logical interpretation and I can solve it. Okay, or what I can do, I can take another instance where what I will do, I will take only one tuple for the maximum value of A in table R. Okay, means this is what I'm saying, that if I do not get success by taking this instance, then I will take this instance, because you can see in this instance I am taking this RA maximum value 2 times, and in this instance I am taking this RA maximum value 1 time. Okay, I hope you are understanding my point. But one thing I can guarantee, that once we consider this instance, once we run these two queries on this instance, then at least we will figure out the behavior of query 1, query 2. Then we can apply the logical interpretation on query 1, query 2, and then we can solve it. Okay, so let's see here. What about S? You can see the maximum value of S does not play any role. Actually S is not playing any role anywhere. Okay, in this query 1, query 2, we do not even have S. Forget about it. Okay, you can see in this query 1, query 2, there is nowhere we consider the table S. Okay, so forget about table S. Now let's solve it. Now tell me, what will be the output of query 1? Let's see query 1 output. And we will also see the query 2 output. So let's see the query 1 output. Query 1 is saying select max A from R. Okay, this is our table R. From R, we need to select max A. Okay, so if I select max A, then what will happen? The answer will be 4. Okay, so here you can see the output of query 1. What that will be? That will be basically 4. Okay, very simple. This will be the output. So you can notice one thing notice, this 4 will not come two times. Please understand. It will not happen that okay 4 4. No, 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 no. It will not happen. Okay, because remember this is aggregate function. Please understand. Here you have select max A. Okay, here this is an aggregate function. From this R, we are just finding the maximum value of A. So here basically the maximum value of A, that is basically 4. Okay, so because of this aggregate function, remember there will be only one tuple in the output. Okay, because of this aggregate function, there will be only one tuple in the output, and the maximum value of A will be in the output, so that will be 4. Okay, I hope you understood. Now let's see query 2 output. In query 2, what we are doing? Select A from R. Where? Okay, this where clause is also there. Where? Remember the where clause will apply tuple by tuple. Okay, yes or no? The where clause will apply tuple by tuple. Okay, very simple. So the where clause will check tuple after tuple. Okay, and you can see one more thing. This is actually a correlated, sorry, this is actually a nested query. You can notice we have query within query. You can see this query within query. But notice one thing, this is actually not correlated query. Okay, this is actually nested query, but this is simple subquery. Notice one thing, this is subquery because this is query within query. This is subquery, but this is simple subquery. Okay, means what it means? It means that it will be evaluated only one time. Okay, this inner subquery, we will calculate it one time, we will evaluate it one time, then that's it. Then we will use the result in the outer query. Very simple. So this is not a correlated nested query here. This is not a correlated subquery here. This is a simple subquery. Okay, so you can see what we are doing here. Select A from R. So means inside this inner subquery, this inner simple subquery, this will select A from R. Means basically the output will be 1 3 3 4 4. Okay, now you can see, look at the outer query. In the outer query, we have select A from R, where there is a where clause. So where clause will apply tuple by tuple. Okay, so let's check for this tuple. Just focus on this tuple. Let's check for this tuple. So for this tuple, you check that A value, is it greater than equal to all, and this is the relation. Okay, here you can see what is this relation. This relation will be 1 3 3 4 4. Okay, yes or no? This output, I can say the output of this inner subquery, this will be 1 3 3 4 4. So you can see what we are doing. Where clause is there, we will check tuple by tuple. So let's check for this tuple. So you can see this A value, is it greater than equal to all? So you can see this one value, this one, is it greater than equal to all these values? No. So definitely this tuple will be discarded. Okay, let's check this tuple. This A value, is it greater than equal to all values? Again, no. So this will be discarded. Let's check this tuple. This value 3, is it greater than equal to all these values? Again, no. So this tuple will be discarded. Okay, let's check this tuple. Okay, now notice, let's check this tuple. This tuple, you can notice that the A value, is it greater than or equal to all these values? Yes. So this tuple will be selected. Okay, this tuple will be selected. So because this tuple will be selected, next, let's see the next tuple also. The next tuple also we will check because the where clause will apply tuple by tuple. So let's check the next tuple. Here also you can see that this A value, is it greater than equal to all these values? Yes. Again, yes. So this tuple also will be selected. And then you can see what we are doing. We are doing select A. Okay, means you can see these two tuples will pass the where clause. These two tuples will pass the where clause. Now we are just selecting A. So in the output, what I will get? I will get 4, 4. This is what I will get in the output. So you can notice that for this instance, the query 1 output has one tuple, the query 2 output has two tuples. So definitely query 1, query 2, they are not equivalent. Query 1 and query 2, they are not equivalent. I hope you understood this. Okay, very simple. Basically, what is happening, let me tell you, it's happening that in this query 1 output, notice the maximum RA value, the maximum value of RA, that we will print only one time because of this aggregate function. The output will contain only one tuple. Okay, yes or no? So very simple. But remember, in this query 2, what is happening? In this query 2, we are checking all the tuples of R, and you can see we are checking that this A value, is it greater than or equal to, all these values? Is this A value greater than equal to all these values? So basically what is happening, let me tell you, the maximum value, of RA, this maximum value basically, it will print as many times as it is present in the original table R. Okay, let me tell you, for example, if you have, let's assume, another tuple 4, 5, then what will happen? Then actually we will get something like this. So you can see that if this maximum value appears more than once, then query 2 output and query 1 output will be different. But remember, if the maximum RA value, in this RA column, if that appears only one time, let's assume, if that appears only one time, the maximum value in this RA column, if that appears only one time, if that does not have any duplicate, then query 1, query 2 output actually will be same. Okay, I hope you understood this point. Overall, I can say query 1, query 2, they are actually not equivalent. Okay, now let me tell you one more thing here. You might be having some curious confusion. See, notice one thing, that in the query 1 output, the output table will have this type of schema, max A. Okay, query 1 output schema, I am telling you, query 1 output schema will be something like this. Okay, max A and 4. But this is query 1 output schema. You can see query 1 output schema, it will have this max A, and this is the schema basically. Okay, I am talking about the schema of query 1 output. And you can see query 2 output schema. Let's see. Query 2 output schema, that you can notice that is actually A. Okay, that is actually A. So you can see like this. So some students might be thinking that the schema is also mismatching. Okay, yes or no? Some students might be thinking that query 1 output schema, query 2 output schema. Okay, because of this. Okay, here you can see, here this max A we are printing, and here A we are printing. Okay, so you can see that the output schema is also different. So some students might be thinking that of course these are not equivalent, but this is not correct way to analyze. Okay, basically the question is not asking from schema point of view, the question is asking from data point of view. Okay, means when we say that two queries are equivalent, what we actually want to say, two queries are equivalent, then what we actually want to say, we want to say that whatever input instances you take, the output instance will be same. Okay, whatever input instance you take, input instances you can take whatever you take, but the output instance must be same. Okay, so basically when we consider two queries to be equivalent, then our focus is on the instance, is on the data, not on the schema. Okay, is this clear? Of course it should not happen that one table is printing three attributes, another query, one query output has three attributes, another query output has six attributes. Of course this should not happen. Okay, the number of attributes, or I can say the number of columns, must be same. But I am just saying that these names, these actually do not matter. This is what I am saying. Okay, of course the number of columns must be same. Here you can see one column, here also one column, but these names, or I can say the attribute names in the output, okay, or I can say the column names in the output, that actually does not matter. Okay, and we only check for the instances, we only check for the data. Here actually these two queries are not equivalent, because for this particular instance you can easily see that the query 1 output has one tuple, the query 2 output has three tuples, so they are definitely not equivalent. I hope you understood. Okay, so this is your method number 1. We have taken instance and we have solved it. But there is another method to solve this question, that is logical interpretation. Okay, what is the logical interpretation of these queries? Let's see. You can see this query 1. This is saying select max A from R. Okay, so this is very easy query. You can see query 1 output. Okay, this is actually very easy. That query 1 output, that will be basically maximum value of A. Okay, in this table R, because remember this attribute A only appears in table R. So I don't have to say that attribute A of table R. Okay, because you can see that this attribute A appears only in the table R. Also in these two queries, we don't care about the table S. Also forget about table S. We don't care about table S in these two queries, query 1, query 2. Okay, we only care about query. We only care about table R. Okay, we don't care about table S. So you can see query 1 output, that will be very simple. That will be just maximum value of A. So it is guaranteed that the query 1 output will have one tuple. Okay, yes or no? It is guaranteed that query 1 output will have one tuple. Okay, and what that will be? That will be the maximum value of this column. Okay, in the table R, in the A column, the maximum value you will put here. Okay, very simple. So there will be one tuple in the query 1 output. But let's see the query 2. You can see in the query 2 what we are doing. Notice, first of all, you look at this inner subquery. This is simple inner subquery. There is no correlated subquery here. Okay, so here you can see that this this is basically your all A values. Okay, yes or no? This is basically your all A values. Very simple. Now what we are doing, notice, we are doing like this. Select A from R. Okay, from R. Where? Because there is a where clause. So this where clause will check tuple by tuple. Yes or no? This checks tuple by tuple. So you can see every tuple of this table R we are checking. Every tuple of table R we are checking. And for every tuple we are checking that the A value, is it greater than or equal to all A values? This is what we are doing. So tell me which tuples will pass this where clause. Which tuples will pass? Which tuples of table R will pass this where clause? Only those tuples will pass this where clause which have A value, which is the maximum A value. Okay, yes or no? Basically, only those tuples will pass this where clause which have A value, which is actually the maximum A value in this RA column. Okay, but notice one thing, that because this where clause is checking tuple by tuple, so all the tuples that will pass, because of those tuples, we will get output. Okay, yes or no? All the tuples that will pass, for those tuples, the A component we will put in the output, because there is no select distinct here. We do not have select distinct here. We have select A here. So all the tuples that will pass, for all those tuples, the A component we will print in the output. Okay, so you can see that if the maximum value, like in this column, the maximum value, if that has duplicates, then definitely this query to output also will have duplicates. So you can see that query 1 output, query 2 output, they can become different. When they will become different? They will become different when this RA column, in this RA column, the maximum value of A, that has duplicate tuples. Okay, that has duplicates. I hope you understood this point. Okay, so basically the query to output, let me write it here. The query to output, that will be like this. That will be like this. Let's assume that, assume assume maximum value, max of this RA column. Okay, max of RA column, let's assume that is T. Okay, let's assume that is T. Now in this situation, what will happen? The query to output will be like this: T, T, T. Okay, and you can see query 1 output, that will be T. Okay, how many times, what will be the number of times? So you can see this will be equal to, I can say, how many number of times. So I can say that as many times, as many times as T appears in RA. Okay, is this clear? Very simple. I hope you understood this point. So this is the complete analysis of this question. But now one analysis let's do. What is that? That is, what can be done? In which situations can I say that these two queries will give me equal result? Okay, so this is the variation. Let's consider this variation. Let's consider this variation, that what should I do so that query 1, query 2 output will be same? What can be done to make sure, to make sure query 1, query 2 outputs are same? So what can be done? So let me tell you the solution 1. The solution 1 is that what you do, the max A value that appears, that has no duplicates, or I can say that appears only once basically. Okay, this is the solution 1, that what you do, let's assume you put a condition, okay, that the max value in RA has no duplicates. Okay, the max value in RA has no duplicates. If it has no duplicates, then of course query 1, query 2, they will give you the same result. Okay, but of course this is not a good solution. Why this is not a good solution? Because you have to put this type of condition, you have to put on the table R, you are putting this type of condition, that okay, that maximum value in RA has no duplicates. Of course there is another solution, that is what you can do, you can make this A primary key. If you make this A primary key, of course that will also work. Yes or no? This A, make it primary key. If you make it primary key, then actually there will be no duplicates in this RA column. This RA column will have no duplicates. So of course the maximum value also will have no duplicates. Okay, but there is another solution. What that? The another solution is that what you do, you can do like this. Here in this query 2, you put select distinct. Okay, basically in this query 2, what you do, in this query 2 you put select distinct. Okay, select distinct A like this, then as it is. Okay, very simple. Basically this you introduce, select distinct. So I hope you understood the complete analysis of this option B. One thing let me tell you, very important thing actually. See, in this solution 3, I am saying that this query 2, if it has select distinct, then they will become query 1, query 2, they will become equivalent. But let me tell you, there is one more point here, that in this solution 3, if you use select distinct, then query 1, query 2 will become equivalent when this table R is non-empty. Means this table R has at least one tuple. Okay, so remember, we also need to put a condition and that the size of R that is greater than equal to 1. Okay, in the solution 3. Let me explain it, don't worry. I am saying that this query 2 variation we are creating. Okay, so you can see, let's create query 3. In the query 3, what we are doing this select, we are doing select distinct, select distinct A, and the rest thing are basically same from R, where, okay, where A is greater than equal to all select A from R. Okay, select A from R. So you already know this. Okay, so let me quickly write it here. Select A from R. Okay, so I am saying that this query 3, let me tell you right now, this query 3 is actually not equivalent to query 1. Okay, let me explain why. So right now, remember, this query 3 is actually right now not equivalent to query 1. Okay, and why? What is the reason? So let me explain that. This query 3 is not equivalent to query 1 because what you can do, you consider you consider empty table R. Okay, what you do, you consider empty table R means the table R is empty. Okay, there is no tuple here. This is your table R and this is empty. Okay, means there is no tuple in this table R. I can say the size of R, the number of tuples in R, that is basically 0. Okay, in this situation, let me tell you, in this situation, what will be the query 1 output? Query 1 output in this situation, when R is empty, when R is empty, then what will be query 1 output? So you can see query 1 is using this aggregate function max a, and remember the aggregate function max, the aggregate function max, sum, min. So basically these aggregate functions except count comma count star. Okay, so except count comma count star, remember these remaining aggregate functions, what they do for empty table. So you can see here the table is empty, then we are doing this max, we are applying this max a, this aggregate function. So for the empty table, the output will be null. For the empty table, the aggregate function will give you output null. So remember query 1 output, that will be actually null, means there will be one tuple and that tuple is null. So remember query 1 output has one tuple, it has one tuple and that one tuple is null. Okay, but look at this query 2 output. Look at query 2 output. What will be query 2 output? You can see in the query 2 from R, where clause is there, where clause will apply tuple by tuple because this, but remember this table R is empty. So ultimately I can say the query 2 output actually that also will be empty. Okay, so remember query 2 output will also be empty. So means there will be how many tuples? 0 tuples. There will be no tuples, 0 tuples. So remember, if your table R is empty, then remember the query 3 and query 1 output, they are actually different. Okay, so I can say that if you create this select distinct, if you make it select distinct, means in this query 2, if you change and if you make it select distinct, then also remember query 3 and query 1 are not equivalent. Okay, because the table R can be empty. If table R is empty, then query 1, query 3 will give you different output. I hope you understood. Okay, and let me explain this point if you forgot about it. In Go classes SQL lectures, we have already seen this. In Go classes summary lectures, also we have seen this. Okay, on the YouTube, you can find Go classes SQL summary lectures. There, all these points we have already discussed. Okay, so you can see actually this point. You can notice aggregate functions on empty table. On empty tables. So remember, when we perform aggregate function, when we perform aggregation on empty table, except count, except count comma count star. Okay, so basically if you perform min, max, sum, avg, average. Okay, so basically if you perform these aggregations on empty table, then you can see the result will be null. Okay, and remember, if you perform this aggregate function like count or count star on the empty table, then the output will be 0. Okay, let me explain it. So you can see, let's assume that this table R is empty. You have R a comma b, and let's assume that this R is empty. Okay, in this situation, if you have this query, let's assume query 1. Okay, let's assume there is a query 1, that is select max. Okay, select max a. Okay, another is sum a, and let's assume count a and count star. Okay, count star. Or what you can do, this sum, let me remove this sum. Okay, because the same behavior, Just like this max, the sum also will give you the same behavior. Okay, or let me write short. Okay, in small letters. Okay, so you can see count, so that I can accommodate count star. Okay, count star. So from R. Okay, so let's assume this is your query. Now let me tell you what will be the output. You can see, because your table R is empty, so actually in the output, what you will get? You will get like this. What you will get in max A, what you will get in sum A, what you will get in count A, and what you will get in count star. Okay, so let me explain. You can see in max A, actually you will get null. In sum A, you will get null. Count A, you will get 0. Count star, that will be 0. See, count star is actually very easy. Count star will always count the number of tuples. There is no exception, nothing. Count star will always count the number of tuples. If the number of tuples is 0, then count star will give you 0. If the number of tuples is 1, count star will give you 1. So count star is actually very easy. Okay, count star, it will always count the number of tuples. Okay, next you can see, if you have empty table, then remember sum, max, min, average. Sum, max, min, average, these aggregate functions, they will output null, and this count A, this will output 0. Okay, so this is a special case of empty table. I hope you understood. Normally, remember, if you don't have empty table, then remember one thing, that max, sum, count, min, average, all these aggregate functions except count star. Okay, except count star, basically count, sum, max, min, average, all these, they will ignore the null values. Yes or no? They will ignore the null values. But remember, when you have empty table, then there is a special case. For empty table, all the aggregate functions except count comma count star, all the aggregate functions, they will output null. Count will output 0, and count star, it will always count the number of tuples. Okay, so it is actually very easy. So I hope you understood this point. Now from this point, you can easily see that this query 3, if I write select distinct, then also query 1 and query 3, they are not equivalent. Okay, so what should I do? If I want to make sure that query 3, query 1, they are equivalent by adding this distinct, query 1, query 3 become equivalent, then what I can do? Then I need to make sure that I need to also give you this condition that R is not empty. Okay, so remember, I can say that if R is not empty, if R is not empty, then definitely query 1 will be equivalent to query 3. Okay, is this clear? But if it is not given that R is not empty, if this information is not given that R is not empty, then remember query 1, query 3, they are not equivalent. Okay, so I can say by default, if you notice, this query 1 is not equivalent to query 3. I hope you understood. Okay, so basically small things I hope you learned from this analysis of option B. Okay, the small things, these are actually very important. Okay, because remember, if you see this query 3 and query 1, they are almost always equivalent, except when the table is empty. When the table is empty, then query 1, query 3, they will give you different result. Okay, yes or no? So that is the reason they are not equivalent, query 1, query 3. I hope you understood the complete analysis. Let's see option C now. In option C, we have query 1, query 2. Query 1 is select distinct A from R, and query 2 is select A from R, group by R. So in this query 2, we have group by clause, group by A, select A. Basically, we have group by clause, but there is no aggregation in the select clause. Okay, so we are using the group by without any aggregation. There is no aggregate function in the select clause when we are using the group by clause. And if you remember in the goclasses lectures, also in the goclasses summary lectures, when we were discussing SQL summary, you can find on the YouTube, you can search goclasses SQL summary lecture. There, I told you one important point, that when you use this group by, This group by clause, when you use without aggregation, here you can see we are not using any aggregate function like max, min, sum, like that. So you can see that when you use this group by without aggregation, then this is useless. And also one more thing, that when you use this group by without aggregation, then it is equivalent to select distinct. Using group by without aggregation is always equivalent to select distinct. This point we have already seen in our lectures, in our summary lecture, if you remember. Okay, but don't worry, this question you can solve if you did not know about this. Okay, I told you that when you use group by clause without aggregation, in the select clause there is no aggregate function here. So when you use group by clause without aggregation, then it is always equivalent to select distinct. Okay, so basically these two queries are actually equivalent. But let's assume you do not know about this point. Then how to solve it in the exam? Very simple. You take a generic instance and you solve it. Very easy. So what we will do? Let's take a generic instance. Remember, in our database, we have two tables. One is table R, another is table S. But you can see in these two queries, we don't care about table S. So forget about table S. Okay, let's only focus on table R. So let's focus on table R. A comma B. Now let me take a generic instance. Okay, you can see, read the queries. From the queries, we can decide what type of instance we need to take. Basically, what type of possibilities we need to cover. So basically, there is nothing here. We have select distinct A. So we can take some tuples which do not have duplicate, some tuples which have duplicate. This type of relation I can take. This type of instance I can take. Okay. So you can see I can take 1, 2. This tuple has no duplicate. I can take, for example, 3, 4, 3, 4. This tuple has duplicate, 2 times duplicate. Okay, I can also take, let's assume like 4, 5, 4, 5, 4, 5. Okay, so I think this will be enough. This is most generic instance from these two queries point of view. Okay, you can see I've taken a tuple which does not have duplicate. I have taken a tuple which has duplicate but frequency is basically 2. I have taken another tuple which has duplicates and frequency is 3. Okay, so basically from these two query point of view, I have taken a generic instance. Now let's see what will be the query 1 output, query 2 output. So let's see the query 1 output. The query 1 output, this is very simple. Select distinct A from R. From this R, select distinct A. Okay, so you can see what will be the output. The output will be 1, 3, 4. This will be the query 1 output. Very simple. Okay, 1, 3, 4. Select distinct A. Now let's see query 2 output. What will be query 2 output? You can see in the query 2, we are having group by clause. Okay, so you can see first, this is the step number 1 in the conceptual evaluation of SQL query. When you evaluate the SQL query, then this step number 1, this is from R. Okay, means you focus on this table R. Group by A, we need to make groups based on A. Okay, yes or no? So in this table R, you make groups based on value of A. So you can see this group will be created. Okay, let's call it group G1. Another group will be created where A equal to 3. You can see here A equal to 1. So this is your group where A equal to 1. Another group where A equal to 3. Another group where A equal to 4. Okay, yes or no? So basically, there are 3 groups because you can see we are making groups for attribute A. Yes or no? Group by A. We are grouping by A. So here you can see that A value 1, A value 3, A value 4. So 3 groups created. Okay, now what we need to do? This is done. From R, group by A, grouping has been done. Now select A. Now what we need to do? Now we need to select A. Remember one thing, very important point. I told you in our lectures also that when you have group by without having clause, there is no having clause with group by, yes or no? When you have group by without having clause, then remember the number of tuples in the output, that will always be equal to the number of groups. Very simple. Okay, so remember one thing. This very easy point you remember, that when you have group by clause without having clause, there is no having clause here. So when you have group by clause without having clause, then then the number of tuples in the output, that will always be equal to the number of groups. Okay, here you have 3 groups. So remember, in the output there will be 3 tuples, 1 tuple per group. When you have group by clause without having clause, then in the output you will have one tuple per group. Okay, very simple point. One more thing, remember here. Here we do not have where clause, but actually, if you have where clause, then remember before making the groups, you apply the where clause, because some tuples can be some tuples can be rejected by the where clause. So those tuples you ignore, and then you make the group. This is a very simple, very easy point, that if you have where clause, let's assume, then remember before making the groups, you apply the where clause. Where clause will check tuple by tuple, then some tuples will be selected, some tuples will be rejected. The rejected tuples you ignore, you throw away rejected tuples. The selected tuples, by the where clause, the selected tuples, on those tuples you make groups. And then remember, if you have group by without having clause, if you have group by clause, then the number of tuples in the output, that will always be equal to number of groups. And I can say that in the output there will be one tuple per group. And if you have having clause, then if you have group by clause with having clause, then I can say that number of tuples in the output, that will be less than equal to the number of groups, because of the having clause, some groups will be rejected. Okay, very simple point. If you have where clause, then some tuples will be rejected, some tuples will be selected. So those tuples which are rejected, you throw them, you ignore them, you throw them, you don't consider them for making groups. Okay, so after where clause, you go to this group by clause. So after the where clause, only for the selected tuples by the where clause, only for those selected tuples, you make the groups. Okay, after making the groups, the having clause, if you have having clause, then this having clause, what it can do, it can reject some groups. Okay, so remember, if you have having clause with group by clause, then the number of tuples in the output, that will be less than equal to the number of groups. But if you have group by clause without having clause, then per group one tuple will go to the output. Very simple. These are very basic, very simple points that we have discussed in our lectures. In the summary lecture on YouTube, you can put go classes SQL summary. Okay, you can find SQL summary part 1, part 2, part 3. In 3 parts, the complete SQL I have discussed. All these points, all these important points, every small point, everything I've covered, you can watch it. Okay, only 3 part, only 3 lectures, and your complete SQL, you will clearly understand the complete, clear, correct understanding of SQL you will get in those 3 parts of SQL summary. Okay, anyway, let's see here. You can see what will be queried to output. You can see from R, group by A, we have done grouping by A, then select A. Now we are selecting A. So you can see per group one tuple will go to the output per group. Okay, so you can see we will get 1, 3, 4. So you can see that for this particular instance, the query 1 output, query 2 output, they are basically same. And remember one thing, this is very generic instance that I have taken. Okay, so this is the reason I can say that this query 1, query 2, actually they are equivalent. Whatever instance you take, they will always give you the same result, the same output. Okay, of course, from this generic instance, you can easily see that query 1, query 2 output, they are basically same. Okay, one more thing, let me tell you. Once you understood this explanation by taking a generic instance, now you also understood the behavior of query 1, query 2. So what you can do now? Now you can apply the logical interpretation. Okay, so what you can do? Now you can logically interpret these two queries. Notice, in this query 1, what you are doing? In this query 1, we are we are selecting distinct A, means the distinct values in the A column. We have this table RAB. So you can see the distinct values in the A column, only those we are putting in the output. Okay, so you can see, for example, if you have, let's assume you have something like this: 1, 1, then 2, 2, then 2, then 3, 3, 3, 3, 4, 4. Okay, like this if you have. Now remember one thing, that in this query 1 output, what will happen? The distinct values of A column you will put in the output. Okay, so 1, 2, 3, 4, like that. The distinct values, very simple. Now notice one thing. In this query 2, what we are doing? First, we are making group by A. So what will happen? If you are making group by A, then it will happen like this, that notice, for every A value, groups will be created. Okay, yes or no, it will happen like this. In this query 2, what will happen? Groups will be created. For example, group 1 will be created for some A value. that a value can be, for example, x. Okay. Now, for another a value, group will be created. Let's assume that is y. Okay. You can see for another a value, group will be created. Let's assume that is z. Okay. Is this clear? Now, you can easily notice that this query one output, what that will be? Query one output, that is distinct a values. Okay, yes or no? So that will be basically x, y, z. But notice one thing. In this query 2, you notice we are making groups by a. Okay, so you can see all the a values which are same, they will be in the same group. Okay, basically all the tuples with same a value, they will be in the same group. All the tuples will be all the tuples with the same a value, they will be in the same group. Okay, yes or no? Because we are grouping by a. Now what will happen? There is group by clause without having clause. So per group, one tuple will go to the output. Okay, yes or no? So you can see we are selecting a. So in this query 2, what will happen? Per group, one tuple will go to the output. Per group, one tuple will go to the output. So we are selecting a. So that is the reason I can say this will be also xyz. Okay, so this is the logical interpretation. Okay, I hope you understood this point, that whatever you do, whatever instance you take, the output of query 1, query 2, that will always be same. I hope you understood. Very simple. Also, let me tell you that important point that I already told you, that when you have group by without aggregation, you can see in the select clause, we don't have any aggregate function. There is no min, max, sum, count, average. Okay, these things also count star. Basically, we don't have any aggregation in the select clause. So when you use group by without aggregation, then it is actually equivalent to select distinct. Means remember, using group by without aggregation, it is actually useless. There is no use of using group by without aggregation, because notice, without aggregation, this group by, it is basically equivalent to select distinct. So instead of using group by, you can just use the select distinct. Okay, I hope you understood this point. The same thing I have written here. You can see group by without aggregation, it is valid. Yes, of course you can use it. Group by you can use without aggregation, that is fine. But it is useless. Why this is useless? Because group by without aggregation is equivalent to select distinct. So why are you using group by? Just use select distinct. Yes or no? Okay, I hope you understood this point. So very simple. You can see here in this query, in this option C also, you can see query 1, query 2, they are equivalent. Why they are equivalent? Because you can see here you have select distinct, and you can see here you have group by, and here you have no aggregation. Okay, yes or no? Here there is no aggregation. Okay, so that is the reason I can say the query 1, query 2, they are basically equivalent. I hope you understood. Okay, very simple. So let me write it here, the general template. Let me write. Okay, so let's see the general template, that is group by without aggregation is equivalent to select distinct. The general template is like this. If you have select from where, okay, and then group by. So let's assume group by a1, a2, and so on, an. Okay, means you can have single attribute, you can have two attribute, you can have any number of attribute. Okay, so very simple like this. Let me use ak. Okay, so you can see that we have these attributes in the group by. So in the select clause also, we must have these attributes. Okay, in the select clause also, we must have these attributes. So very simple point. Now you can see from table R, okay, where some condition is there, some condition C, okay, or I can say some condition, okay, let's use this. Okay, so now let's see, this will be equivalent to what? You can notice here, notice one thing, there is no aggregation in the select clause. We are using group by without aggregation. When you use group by without aggregation, then this query will be equivalent to, always equivalent to what? Select distinct. Means you forget about group by, just use select distinct. Just use select distinct. Just use select distinct. That's it. Okay, select distinct A1, A2, and so on, AK. AK from R, where condition. Okay, that's it. Very simple. I hope you understood this general template. So remember this general template. This is actually very useful general template sometimes. Okay, I hope you understood. So remember, group by without aggregation is valid but useless, because when you use group by without aggregation, then it is equivalent to select distinct. So you can just remove this group by and you can use select distinct. Okay, I hope you understood. So these two queries, they are always equivalent. What is the usefulness of group by? The usefulness of group by comes by using the aggregation. When we want to do aggregation group by, like group wise aggregation, if you want to perform, if you want group wise summary, aggregation means summary. So if you want group by summary, then group by clause will be helpful, useful. But if you do not have, if you do not want summary, okay, if you do not want aggregation, then this group by, it is valid. You can use it without aggregation, you can use it, but it is useless. Okay, it will be equivalent to select distinct. That's it. I hope you understood this. And remember, all these points we have discussed in Go classes SQL summary lectures, in the SQL course, in the Go classes DBMS course. So if you do not have Go classes DBMS course, then what you can do, you can just search Go classes SQL on YouTube. Okay, and you can see this SQL complete summary part 1, part 2, part 3. These three parts you can watch, and your complete SQL you will understand in a clear way, complete way, correct way. Okay, all the concepts, everything is covered here. Also you can see there are gate pyqs of SQL part 1, part 2. So in this playlist, basically there is a playlist. Okay, in this playlist you will find SQL complete summary, also SQL gate pyqs part 1, part 2. These things also you will find in this playlist. I will provide you the link in the description also, in the pinned comment also. But remember, if you do not find the link, then you can just search on YouTube Go Classes SQL. Just search it and you can find this playlist and you can learn from it. Okay, you can watch it. I hope you understood. Now let's consider this query D also. Means option D. Let's now consider option D. Query 1 is saying select distinct A from R, group by A, having max be greater than 10. And the query 2 is saying select distinct A from R where B is greater than 10. Okay, so first let's see the method number 1, that is method number 1. Which method is that? That is taking a generic instance. Okay, taking a generic instance. So let's take a generic instance and then let's see this query 1, query 2, what will be their behavior. So here you can see that we only care about table R, even though we have table R comma S. Okay, you can see in our database we have table R, we have table S. But in this particular option D, you can see in this option D, in these two queries, this table S we don't care about. We only care about table R. Okay, so let's focus on table R. Now let me take a generic instance, and remember which type of tuples I should take. That will be told by these two queries also. You can see these two queries are focusing on B greater than 10. So I need to take some tuples where B less than 10. I will take a tuple where I will take a tuple where B is 10 and some tuple where B is more than 10. Okay, are you getting my point? You can see here, because these two queries are telling me that B greater than 10 is playing some role here. So I will take some tuples with B less than equal to 10. I will take some tuples with B greater than 10. Also notice max B greater than 10. So this is also playing some role here. So the maximum value of B, I will take multiple tuples for that. Okay, are you getting my point? So you can see basically I'm making a generic instance, I'm making based on these queries. Okay, so that I can cover all the possibilities, so that I can get my answer. Very simple. So here what I will take, I will take some tuples with b less than equal to 10. Okay, so for example what I can do, I can take like 1 2. Okay, then I can take like 3 4 3 4. Okay, or if you want 3 10 3 10. Okay, even though remember b less than equal to 10, all tuples are basically similar for me. Okay, you can see here, because we only care about b greater than 10. So this 10 will confuse you. That is the reason you forget about this 10 and you take 4 4. This 10 will confuse you, because remember anyway the equality to 10 is not there here. Okay, nowhere it will impact, because we only care about greater than 10, greater than 10. So for me, greater than 10 is one category, less than equal to 10, that is one category. In the less than equal to 10, I can take any value. Okay, so you can see this tuple does not have duplicate, this tuple has duplicates. Then let me do one more thing, that let me take some tuples where b is greater than 10. So let me take, for example, this tuple like 4 11. Okay, this does not have duplicate, and let me take this has duplicate. You can see, so this tuple has duplicate, this tuple does not have duplicate. I think I have covered, I've taken the most generic instance. Okay, at this moment you can see, for the maximum value of b, that is 12, for that also I have taken multiple tuples. Okay, so you can see, based on these two queries I have taken the most generic instance, and hopefully this generic instance will give me the answer. Okay, very simple. So let's see the query 1 output, what that will be. Query 1 output. Query 1 output, you can see, that is select distinct A from R, group by A, having max B greater than 10. Notice one thing. First, I am finding this query 1 output. In the query 1 output, you can see what the conceptual evaluation of SQL query. Whenever SQL query is given to you, then the step number 1, that is this from clause. Okay, so from R, we need to focus on this table R. Then group by, we need to make group by A, grouping by A. So you can see, let's make grouping by A. So you can see here A value is 1, here A value is 3, here A value is 4, and here A value is 5. Okay, so this type of grouping also we have done. Very simple, group by A we have done. Now let's see the next, that is, you can see, after making the grouping, we have having max b greater than 10. Remember this having clause, it works group by group. Okay, so remember one thing, this having clause, this works group by group, group by group. Okay, group by group. So remember this having clause, basically it will select some groups and it will reject some groups. Okay, so you can see we are saying that after grouping by A, after grouping by A, some groups will be chosen, some groups will be rejected. Which groups will be chosen? You can see where max is, max b is greater than 10. So you can see this group will be, this group is gone, this group is gone. Okay, you can see where max b, where max b is greater than 10. Okay, so here I can say that this will be, this group will be chosen, this group will be chosen. I hope you understood. Actually, let me take one more thing, let me do one more situation, that let me take 6 comma 12 also. Okay, let me take 6 comma 12 also, because here you can see we are doing grouping by A, but we are choosing the groups based on max b value. Okay, yes or no? So let me take this type of tuple also to cover all the possibilities. Of course, without this also we can check, don't worry. Okay, but I think that, okay, maybe this type of tuple also we can take. Okay, and maybe one tuple like this also I can take, for example. Okay, let me take where I have 5 comma. So what I'm saying, see, okay, don't worry, I will do that. Okay, I will do that. Right now let's just consider this instance. Okay, even let's forget about it. Okay, don't worry, I will explain what I'm saying. saying. What I'm saying, I will explain. But right now, let's just consider this instance. Okay. So here you can see that these two groups, they will pass by the having clause. Okay. So these two groups are selected, I can say. Okay. By the having clause, these two groups have passed and these two groups have failed. Now what we will do? The groups that have passed, now remember, per group one tuple will go to the output. Okay. Now what we are doing? Now we are doing select distinct A. Okay, so you can see now select distinct A. So here in the output, what we will get? Per group, one tuple will go to the output. Okay, so we will get 4 comma 5. This will be your output. I hope you understood. One more thing, remember, here actually this distinct is useless, because remember, if you don't have this distinct, then also per group one tuple will go to the output. Yes or no? So actually this distinct, because we are already grouping by A, then you are using distinct A. So this distinct A, this distinct is actually useless here. Okay. If you remove this, then also this query 1 will give you the same output. Means I can say from the query 1, if I remove this distinct, then also you will get equivalent query to query 1. This is what I'm saying. Okay. So remember, this is actually useless, redundant, I can say. I can say it is redundant. Okay. Means if you don't have this, if you don't have this, if you don't have this, remember, let's remove. So if you don't have this, then also the query 1 will be equivalent. If you don't have distinct, if you have distinct, then both the queries are actually equivalent. Okay, because per group one tuple will go to the output. You are grouping by A and you are also printing A. Okay, so per group you can see one tuple is going to the output. I hope you understood. Now what about query 2? Query 2 output, you can see in the query 2 it is very simple. There is a where clause. Where clause will work tuple by tuple. Yes or no? This works tuple by tuple. Tuple by tuple. Okay, so you can see that we have from R where B greater than 10. So you can see here B greater than 10. Okay, so what you are doing? You are doing select distinct A. Remember, these three tuples will pass because here B greater than 10. So these three tuples actually will pass. Okay, and now you are selecting distinct values of A. Okay, so what you will get? You will get 4 5. So did you notice that for this particular instance we got the same output? Okay, but some more possibilities, let me try. Actually in this instance I did not cover all the possibilities. Now let me cover all the possibilities. What I will do, notice, I will take this type of instance where I have, for example, like this. I have 1 2, I have 3 4 3 4. Okay, so far it is fine. But notice what I will do. I will take this type of situation that 5 11 5 12. Okay, 5 12. Okay, like this. This is what I will take. Also what I will take, notice, I will take 6 12, then 6 13. Okay, then let's assume 7 14. Okay, like this. Now I think that we have covered all the possibilities in this instance. Okay, notice what we will do now. In this query 1, what will be the output? In the query 1, from R, this is the table R, from R, grouping by A. First you make groups by A. You can see we are doing grouping by A. So value of A is 3, value of A is 1. You can see value of A is 5, value of A is 6. Okay, and value of A is 7. So these are the groups that will be created. Next you can see the having clause. It will work group by group. Okay, some groups will be selected, some groups will be rejected. So you can see here we have we are basically selecting those groups where max B is greater than 10. Okay, so you can see that this group will be selected, this group will be selected, and this group will be selected. One more thing here, let me do like this, that instead of 5 11, let's take 5 2. Okay, and here also instead of 6, instead of 7, yes, yeah, everything is else is fine. Yes, let's do this. So you can see now what will happen? Some groups will be selected by this having clause, some groups will be rejected. So you can see we are selecting those groups those groups will pass this having clause where maximum b value is greater than 10. So here you can see here maximum b value is actually greater than 10. Notice there is some way, there is a tuple where b value is less than 10, but the maximum b value that is greater than 10. Okay, so those this group will pass, this group will pass, this group will pass. Okay, so in the query 1 output, what you will get, these three groups will pass the having clause. So now per group one tuple will go to the output and you are printing the value of a. This distinct, this is a redundant, I already told you. Okay, so you can see that the output will contain 5 6 7. Per group one tuple will go to the output. Okay, what about query to output? You can see query to output, that will be those tuples where b value greater than 10. So you can see those tuples, these are the tuples, remember these are the tuples where b value is greater than 10. Okay, so now we are printing distinct a, so that will be 5 6 7. Again you can see that these two queries, they are giving me same output. Okay, I hope you understood this point. But remember, after taking these instances, now we understood the behavior of these queries. So now we can apply the logical interpretation. That is the good thing. Okay, if you do not understand what these queries are doing, then you take then you take an instance. Okay, then you try to understand what these queries are doing. But now after taking the instance, now we have understood what these queries are actually doing. Okay, so let's see here, this query 1, query 2, what they are doing. Notice, first let me tell you what this query 1 is doing. This query 1, or first let's see the query 2, because that is easier. So you can see this query 2, what this is doing, select distinct a where b greater than 10. Okay, so it will happen like this. This query 2, what it will do, from your table, from your table you can see all the tuples where b greater than 10, all those tuples where b greater than 10, those a values, only distinct a values corresponding to those tuples we are printing, okay, in the output. So you can see that query 2, what it is actually doing, query 2 is doing something like this. Notice, notice one thing, something nice I'm going to prove. Every output in query 2, that will also be in the output of query 1. Every output in query 1, that will also be in the output of query 2. Let's prove this. Okay, you can already see that there is a distinct here in the query 2. So definitely all the values in the output will be distinct. Okay, and in the query 1, because you are making groups, you are grouping by a, and then there is select a. Okay, so this distinct is actually redundant. Whenever we use this group by, then actually this distinct is always redundant. Okay, this distinct, this is actually redundant whenever you use group by. This is what I'm saying. Okay, now let's see something beautiful here. I'm saying that whatever value will print in the query 2 output, that value will also come in the query 1 output. Let's prove it. I'm going to prove that. You can see, let's prove part 1. Okay, you can see I will prove that this query 2 output will be a subset of query 1 output. Okay, means every value in the query 2 output, that also will be in query 1 output. Okay, how to prove it? It's actually very easy. You notice in this query 2, if some value is there, let's assume some value y is there, then what it actually means, just tell me a simple point. If y is there, then you can notice that in the query 2, if you have this y value, okay, in the output of query 2, if you have this y value, what it means? It means that from R where b greater than 10, only those tuples where b greater than 10, only those tuples will pass this where clause. And you can see in those tuples where b greater than 10, in those tuples, the distinct a value we are printing in the output. So you can see that if this value of a is in the query to output, then definitely there is at least one tuple where you have y, also the b value is greater than 10, maybe like this. At least one tuple is like this. Okay, yes or no? This type of tuple is definitely there, guaranteed. Now notice in the query 1 what will happen. In the query 1, notice what we are doing. We are grouping by a. If you are grouping by a, then there will be a group where this y value will be there. Okay, yes or no? Because we are grouping by A, so definitely there will be a group. You can see this type of group will be there. This type of group will be there. Okay, let's call it, for a moment, let's call it group Y. Okay, group Y. Is this clear? Because you are grouping by A, so all the tuples where A value is Y, all the tuples where A value is Y, those tuples will come in this group. Correct? Okay. Now you can notice this Y12 is also there here. I don't know what are these values. I don't know these remaining values, but this Y12 is here. Now notice what we are saying. We are saying that having max B is greater than 10. Tell me here, what will be the max B value? What do you think? Very simple point I am asking. I am asking, what do you think? What is the max B value here? This is A value. This is B value. I am asking, what is max B value here? You can see already there is a tuple with B value 12. So max B value is definitely greater than equal to 12. Yes or no? In this group GY. Okay, yes or no? In this particular group GY, the max B value is definitely greater than equal to 12 because already we have a tuple with the 12 value. So the maximum value of B cannot be less than 12. In this group, the maximum value of B cannot be less than 12. It will definitely be greater than 12. If it is greater than 12, then yes, it is greater than 10 also. So you can see for this group will pass the having clause. Yes or no? This group passes having clause. Having clause. If this group passes having clause, then what will happen? Then per group, one tuple will go to the output. Now you are printing the A value. So you can see that this will go in the output. Okay, yes or no? Very simple. This in the output of query 2. In the output of query 1. So you can notice what we have done. We have proven a formal proof I have given to you that every value in the output of query 2, that is also in the output of query 1. This is the formal proof we have seen. I hope you understood. Now let's see the proof part 2. Okay, proof part 2. In this part 2, what we will do? Now I will prove that the query 1 output. Now I will prove that query 1 output is subset of query 2 output. Okay. Means in query 1 output, if there is some value, you can see what is the query 1 output. That is basically value of A, distinct values of A. Okay. Of course, this distinct is actually redundant because of this group by. When you are using group by, then this distinct is redundant. Okay. So you can see this simple point you can write in your notes. Maybe you can see that when you are using group by, whenever we are using group by, then we already know that from every group that will pass the having clause. Okay. After the having clause, basically all the remaining groups, all the groups which are passing the having clause, from those groups, one tuple per group will go to the output. One tuple per group. So you can see that is the reason this distinct is actually redundant whenever you are using group by. Okay, very simple. So let's see. In the query 1, let's assume there is a output Z. Okay, let's assume in the query 1 output, we have this Z value. Okay, what it simply means? It simply means in this query 1 output, if you have this Z in the output, if you have this Z, what it means? It means there is a group with A value Z. Okay, definitely there is a group. You can see there is a group. There is a group where A value is Z. Okay, and this group is passing the having clause. Yes or no? Because in the output, if you are having this Z in the query 1 output, we have this value Z. It simply means that there is a group by the A value Z. There is a group by A value Z which is passing the having clause. Then because this group is passing the having clause, then this value is going to the output. So definitely this is passing the having clause. What it means? If this is passing the having clause, what it means? It means that the max b value is greater than 10. Let's assume that this is the max b value and this is greater than 10. Maybe the remaining values are, the remaining values can be anything. I don't care. But the point is that there is at least one b value which is greater than 10. Yes or no? This type of situation is there. Now notice one thing. What will happen in the query to output? So if you have this type of situation in your table R, then you can see that this tuple will pass the where clause, where b greater than 10. So this tuple will pass the where clause, and that is the reason I can say this z will go to the output. Okay, that's it. So this is what we have proven, that every value in the query 1 output will also be in the query 2 output. Also we have proven that every value in the query 2 output will also be in the query 1 output. Also we already know, because in this query 2 we have distinct and in this query 1 we have group by. So duplicates will never be there in the output. Okay, so basically because of these three things, what three things? The first thing, in the query 2 we have distinct, in the query 1 we have group by. So in the output of query 1, in the output of query 2, there will be no duplicates. This is one thing. Second thing, we have proven that every value in query 2 output will also be in the query 1 output. Also we have proven that every value in the query 1 output will also be in the query 2 output. So overall we have proven that whatever instance you take, whatever table R you take, whatever instance of table R you take, then remember query 1 and query 2, they are always equivalent. They will always produce the same output relation. I hope you understood. Okay. So very simple. So I hope you understood this. So this is the complete analysis of this particular SQL question. Of course, I have taken a lot of time, but I hope you understood some small things. It's like SQL revision. If you felt like a SQL revision, then please let me know in the comments, because a lot of time I have spent in the complete analysis of this particular SQL question in AIMT2. Okay, so you can see I'm continuously speaking. Okay, I hope this has added some value to your preparation. Maybe SQL revision, maybe some option, the complete analysis of some option you liked. Okay, basically just let me know your feedback about this particular question. Please let me know. It is very important, because you can see a lot of time I have spent in the complete analysis of this question. So just put a comment. I think you can put just one comment. You just let me know about your feedback about this particular question. Was this was this complete analysis helpful, or was it unnecessary for you? Okay, maybe it was unnecessary for you. Okay, so just let me know. Now let's move on. Let's solve this question from pipeline topic in COA subject, computer organization and architecture. Consider a CPU with 5-stage pipeline structure. These are the 5 stages: IF, ID, EX, memory, and write back. So you can see these are the 5 stages of pipeline with separate data and instruction memory. What this line actually means, let's see. We have a pipeline structure with separate data and instruction memory. What it actually means? It means that we have a separate data memory, we have a separate instruction memory. So in the same cycle, one instruction can access the data memory, another instruction can access the instruction memory. So basically this line means that because of hardware limitation, there will be no delay. Okay, this line is saying that we have separate data and instruction memory, data memory separate, instruction memory separate. So in the same cycle, if one instruction want to access data memory, if another instruction want to access instruction memory, then they can do it in the same cycle. In the same cycle, two different instructions, they can access, one of them can access data memory, another can access instruction memory. So basically because of hardware limitation, because of hardware shortage, there is no delay, there is no stalls. This is what this line is saying. Or I can say that basically there is no structural hazard. Okay, There is no structural hazard. Very simple. Now let's see the next. The next line is no data forwarding mechanism. What it means? See, data forwarding mechanism, what it means? Data forwarding mechanism says that as soon as the required data is available at some place, then you access it. Okay. But remember, if you do not have data forwarding mechanism, what it means? Let's assume I need to read data from the register 2. Okay. And that data is right now not available in the register 2, but it is available somewhere else, maybe in some entry stage register. Between stages we have register, so maybe in some entry stage buffer, maybe this data, this value is actually available. But remember, because there is no data forwarding, so actually we cannot use this value from that entry stage buffer. We have to wait until this value is returned to the register, to the required register. For example, if I want to read from register 2, then I will wait until this value is returned to the register 2. Okay, yes or no? From the register 2 I can read it, but I cannot read it from the entry stage buffer. Okay, this is what it means. I hope you understood. So remember, there is no data forwarding mechanism. It simply means that I need to wait until the data is present in the required register, until the data has been written to the required register. Okay, very simple. Now the next line is saying that writing to the register bank on the rising edge of the clock and reading on the falling edge of the clock means in the same cycle we can write to the register, also we can read from the register. Okay, basically what this line is saying, this is the split phase, I can say. This is called split phase. What it means, let me tell you. It simply means like this, that in the same cycle, let's assume this is a cycle. Okay, you can see we are saying that writing to the register bank, or I can say we are writing to the register on the rising edge. This is the rising edge. Okay, and this is the falling edge. So you can see we are saying that we are writing to the register on the rising edge, means here we are writing to the register, here register write is happening, here register write is happening. And you can see that we are reading on the falling edge, means here we are reading from the register, we are reading, register read is happening. Okay, so what is the benefit of this? This is called split phase. Okay, it's like we are splitting a particular cycle. You can see this particular cycle we have split. You can see that in the first half you write into the register, in the second half you read from the register. But what is the benefit of this? The benefit is like this: if some register is writing to the to sorry, if some instruction, see, the benefit is like this. Let me tell you. Let's assume there is an instruction, some instruction I, and there is an instruction J. Let's assume this instruction is writing to register 2. Okay, and let's assume this instruction like this. Let me put dot dot. Okay, or not necessary. Basically, it can be consecutive instruction also, and it may not be consecutive also. Okay, that we will see. Don't worry. When we see this actual question, then it will become clear. But you can see this point. What is the benefit of this split phase? This is what I'm saying. You can see, let's assume that this instruction I is writing to register 2, and let's assume that this instruction J need to read from register 2. Okay, so now you can notice what this register I can do. This register I can write to the register 2. This, what this instruction I can do, this instruction I can write to the register 2 in the first half of the cycle. And then you can see in the second half of the cycle, this instruction J can read this register 2. This is the benefit, that in the same cycle this instruction I is writing to the register 2, and in the same cycle this instruction J is reading from register 2. Okay, so this is the benefit of split phase. Let me tell you one more thing, that the complete pipeline lectures, all the pipeline lectures, the complete pipeline concept we have put on the goclasses YouTube channel. On the YouTube you can search goclasses pipeline. Okay, just search it. Then there are 5 lectures of pipeline, and let me tell you all the concepts I have discussed there. There are many misconceptions among many students. Like many students, they don't understand data dependency versus data hazard, what is split phase, Okay, and many more concepts. So let me tell you, there are 5 lectures of Go classes for pipeline. All these 5 lectures are available on the YouTube. You search Go classes pipeline on the YouTube, and you can watch these 5 lectures. Just 5 lectures, and there is a guarantee that in the gate exam, whatever pipeline question comes, you will be able to solve it. Okay, just 5 lectures, nothing else. Now, so let's come back to this question here. I hope you understood everything that is written in this question. Okay, so you can see we are writing to the register in the first half of the cycle, and we are reading from the register in the second half of the cycle. There is no data forwarding. So if an instruction needs to read from some register, then it need to wait. Then the instruction needs to wait until the data has been written to that particular register. Okay, very simple. And there is separate data in instruction memory. It simply means that there is no structural hazard, and I can say that one instruction can access the data memory. In the same cycle, another instruction can access the instruction memory. Very simple. I hope you understood. Now let's consider this sequence of instructions. You can see the following set of instructions. Let's consider. We will see the meaning of these instructions, don't worry. But the question is asking, each stage takes exactly one clock cycle to complete. What it actually means? See this line. Each stage is taking exactly one clock cycle to complete. It actually means that if there is no issue, if there is no dependency, if there is no stall, if there is basically, I can say, if there is no dependency, then in that case, remember, every stage is basically completing its work. Every stage is completing its task in one cycle. Okay, this is what the point is, that every stage will complete its task in one cycle. Very simple. How many clock cycles are required for execution of this code? This code is given to you. Now let's understand this code. But before that, let's understand the 5 stages of the pipeline. Okay. So these are standard 5 stages of the pipeline. This is a standard 5 stage pipeline. Let's see the meaning of all these stages. So you can see what is this IF stage. IF means instruction fetch from the instruction memory. Okay, we will fetch instruction from the instruction memory. So you can see a 5 stage pipeline CPU has the following sequence of stages. The first stage, that is IF, that is instruction fetch from the instruction memory. Then we have RD, or I can say register read, or I can say decode. You can also call it ID. Okay, instruction decode. So what is this instruction decode stage? In this, we decode the instruction. Also, we read the source register. Okay, the source register values we read in this stage. Is this clear? If some instruction needs to read from a register, then in this stage we will read the source register, we will read in this stage. I hope you understood. So you can see this is ID, or I can say RD stage, instruction decode and source register read stage. And next you have EX. This is execute stage. In this, we basically perform the ALU or logical operation. Okay, whatever logical or arithmetic operation we need to perform, for example addition, multiplication, like that also we will perform in this stage. Basically in this stage we use the ALU. And what ALU can do, it can perform the arithmetic and logical operations, so those we will perform in this stage. One more thing, in this stage, in this execution stage, we also compute the address. Which address? We compute the address for load and store instruction, because actually there is a next stage. Let me explain the next stage, then it will become clear what I mean by address computation. So you can see there is a next stage, that is memory access stage. Memory access. In this stage we can access the data memory. Okay, here remember, this is memory access stage, and here basically this is the data memory access. Here we access the data memory access. Notice one thing, in this IF we are accessing the instruction memory, instruction fetch from the instruction memory, and here we are accessing the data memory. And actually this stage is used by the load and store instruction. Okay, only load and store instruction, they use this stage. Okay, in this stage what we do, we access the data memory for read and write. Okay, so the load instruction will read from the memory, the store instruction will write in the memory. So this stage is used by load and store instruction. Load instruction will read from the memory. Store instruction will write in the memory. Very simple. So you can see that this memory access stays here. We perform the load or store if needed. And one more thing, like who will tell us this memory address? This data memory we will access the load and store instruction, load instruction, store instruction. They can access the memory, the data memory they can access, but which address in the main memory, or I can say in the data memory, which address they will access? So you can see that address computation will be done in this EX stage. This is what I'm saying, that in the EX stage, we will perform the ALU operation, arithmetic operation, logical operation. These operations we will perform. Also remember, the address computation we will do for the load and store instruction. For the load instruction, store instruction, the address computation, the data memory address computation we will do in this stage. And on that address will be accessed by the load instruction, by the store instruction. I hope you understood. The other instructions, for example, addition instruction, basically except load comma store, the other instructions they will not access this stage, or I can say they will not use this stage. Of course they will go through it. Okay, every instruction, remember, every instruction will go through all the stages. Every instruction has to go through all the stages, but except load comma store instruction, all the remaining instructions, they will not do anything in this stage. Okay, in this stage they have nothing to do, but they will go through this stage also. Okay, very simple. Now you can see there is last stage, that is write back. In this what we do, we write in the register, means the destination register. We write in the destination register. Very simple. You can see in the second stage where we are decoding the instruction and we are reading from the register, here we read the source register, and in the write back we write in the destination register. So this is the explanation of all the stages. I hope you understood. Okay, now let me explain these instructions also. So you can see these are actually standard instructions. Okay, so you must know the meaning of these instructions. So here you can see the first instruction, I1. Let me explain it. The instruction I1. The instruction I1 is basically load instruction. Okay, you can see this instruction I1. This is basically load word. Load word. Okay, so in short, it is called LW. LW. Okay, load word, or I can say load instruction. So basically, this instruction one, I1, this is basically load instruction. It is load instruction. Okay, and what it actually means, these dollars, these are basically the registers. Okay, so remember when we write, for example, $6, this is basically same as R6. Okay, $6, this is basically same as register R6. So dollar is representing the register number. So you can see, and this is standard. You might be thinking, how do I know that dollar represents register number? The dollar represents register. So let me tell you, this is standard. Okay, it's not something that needs to be given. Of course, they can give it. Okay, they can give it. If they give it, it is very good thing. But you must know. Okay, these things are standard things. That is the reason I did not give. Okay, I could have given in the question that dollar represents register. Okay, I could have given in the question that LW means load, SW means store. All these things I could have given, but I wanted you to know. I want you to know that these are standard things, so you must be aware of them. Okay, is this clear? So you can see in this instruction one, what we are doing, we are using the load instruction. This instruction one is the load instruction. Load means from memory we are reading. Okay, so from memory we are reading and we are putting in some register. So basically it is like this, that in the register 2, okay, in the register 2, what we are doing, it is like this. Let me tell you, in the register 2 basically we are storing, which value we are storing in the register 2. I should not use the word store because store is a separate instruction. Store means we are writing to the memory. So I should use the word load. Okay, basically in this register 2, what we are loading in this register 2, very simple. You can see this memory content. Okay, which memory content? So you can see the content, memory content at this address. The address is 100 plus the content of R5. Okay, I can say R5 like this. I hope you understood. So very simple. I am saying that in this instruction 1, what we are doing, we are loading in the register 2. What we are loading in the register 2? We are loading the memory content at this address. At this address. This is the address. At this address, the memory content, we are loading in R2. I hope you understood. Okay. So you can see content we are loading in R2. Very simple. What about this I2? Let's see I2. This is simple add instruction. Okay. So what is destination? What is source? Let me tell you, this is also a standard thing that first we write destination. Okay. This is most commonly used convention. So if nothing is given to you in the question, if they do not mention which of them is register, which of them is source, which of them is destination, in the question if they do not mention which register is destination, which is source, then remember this is most widely used convention that we write the destination register on the left hand. Okay, so you can see that here what you are doing in the register 1, in register 1 we are putting the value basically R2 plus R3. Okay, we are adding R2 plus R3, and then we are storing, then we are putting this value in R1. Very simple. Okay, then I3, this is also very simple. In I3 what we are doing, in I3 we are doing like this, that in R3 R2 minus R1. Okay, R2 minus R1. Okay, what about I4? Let's see I4. I4 is store word. Okay, so let me explain. Here you can see this is store word. What it means, we are storing in the memory. Okay, so in the memory we are storing. So remember this R2 value, we are storing in the memory, and at which address? The address will be 50 plus content of register 1. Okay, so you can see 50 plus content of register 1. Okay, at this address I can say this is the address, this is the memory address. This is the memory address. At this address, remember, we are putting R2. Okay, so I can say that this is the memory address. So I can say in the memory at this address, we are putting the content of R2. I hope you understood this point. Okay, very simple. Now the remaining are very easy. This is I5. So in I5, what we are doing? In this instruction I5, we are doing in R2, we are putting R3 plus R4, R3 plus R3, R3 plus R3. And in this I6, what we are doing? In R2, we are putting R2 minus R4. Okay, so that's it. I hope you understood. So we have seen the meaning of all these instructions. Now, let's solve this question. Now, what this question is asking, that for this following set of instructions, for this sequence of instructions, what we need to do? We need to find how many clock cycles will be required for the execution of this code in this 5-stage pipeline CPU. Every stage will do its work in one cycle. Every stage will complete its task in one cycle. Okay, so actually let me do one thing, that for all these instructions, let me write what is their source register, what is their destination register. Okay, that is very important. Okay, so you can see that on one side I will write the instructions, and on one side I will write like what are the source registers, and destination registers. Means from which registers they are reading. Okay, basically source registers means from these registers we are reading, yes or no. Okay, from these registers, from these registers we need to read, registers read, and in these registers, or I can say in this register, we need to write. In which register we need to write? Okay, so let's see. You tell me quickly. What about this instruction 1, instruction 2, instruction 3, instruction 4, 5, 6? Okay, so let's see here. You can see in this instruction 1, you can see we are loading in register 2. So in register 2, actually, we are writing. In register 2, actually, we are writing. And remember, we are reading. You can see we are reading from this register 5, yes or no? Okay, remember, this register 5 value plus 100, this will be the memory address. We will go to this memory address. That value we will load in the register 2. But overall, the point is that this instruction I1, it will read from register 5. It will write in register 2. Okay, yes or no? Very simple. Now let's see instruction I2. Instruction I2 will read from R2, comma R3, and it will write in R1. Okay. Now let's see this instruction 3. Instruction 3 is writing in R3, and we are reading from R2, R1. Next, what about instruction 4? In the instruction 4, you notice one thing, that R2 value we are storing in the main memory. So there is no destination register here. We are not writing to any register. Okay, we are not writing to any register. Please understand. Look at this I4, this store instruction. This store instruction is not writing in any register, but we are writing in the memory. So I can say there is no destination register here. What are the source registers? R2 also, R1 also, because this R2 value we will store in the main memory. And also this R1 register also we are reading from the R1 register, so that we can calculate the address of the data memory. Yes or no? Very simple point. So remember, in the store instruction, in this store instruction, or I can say in the store instruction, in store instruction we do not write in the register. Okay, so I can say the destination register, that is basically nothing. Okay, very simple. Now let's see the next, that is I5. Here in I5, what we are doing, the destination register, that is R2. I6 also, the destination register is R2. And the source, or I can say the registers from which we need to read, that is R3 for I5. And you can see R2, comma R4 for I6. Okay, so very simple. I hope you understood. Now let's solve this question. So for this sequence of instructions, we need to check how many clock cycles will be required for the execution. So what you can do, you can make the timing diagram. Now it is actually very easy question. So let's see this question. What I will do, notice, I will make a timing diagram. Okay, so it is like this. We have how many stages? 5 stages. Okay, so I will do like this. You can see how many stages we have. These are the stages. Okay, let me write like this, that we have IF stage, we have ID, we have execute, we have memory, data memory, and then we have let me also like do like this, then we have here write back stage. Okay, so these are the stages. Very simple. Okay, now let's see. In this sequence of instructions, this is the sequence of instructions. You can see this is the sequence of instructions. So first the instruction I1, instruction I1 is coming now. Okay, so let me write. You can see instruction I1 will be in the instruction fetch stage. Yes or no? Very simple. Okay, I'm telling you everything now. You can see that first we will fetch the instruction I1 from the instruction memory. This instruction I1 we will fetch from the instruction memory. This will be done in the IF stage. Okay, now what the next thing? The next thing is that this I1 will go to ID stage, because remember, every stage is doing its work in one cycle. Already this is given to you, that every stage is doing its work in one cycle. So remember, this instruction fetch from the instruction memory, this will be done by the IF stage, and IF stage will carry out its task in one cycle. So you can see in one cycle this task is over. Now this instruction I1 is going to the next stage. In the next stage, what we will do? We will read from the register. Also, we will decode. Instruction decode and register read. So here you can see in this stage, we will read the source register. Okay, next you can see this stage will also do its work in one cycle, because every stage is taking one cycle for to complete. Yes or no? Every stage is taking exactly one cycle to complete its task. So you can see this I1 will go to the execute stage, then I1 will go to the MEM, then I1 will go to the next stage, and here I can say that this I1 will be out. Okay, yes or no? Here you can say, so how many cycles so far? So far I can say that cycle 1 2 3 4 5. So it took total 5 cycles for instruction I1 to complete. Instruction I1 has completed, because remember every stage is doing its work in one cycle. Okay, so instruction I1 we are fetching, we are decoding, and we are reading the source register. Then what we are doing, notice in this stage what we are doing for instruction I1. For instruction I1, in this stage, in this execute stage, what we are doing, we are basically computing the address. Okay, we are computing the address, that is 100 plus R5. We are reading this R5. You can see we are reading this R5 here, because here we will read the source register. So we are reading the R5 in this stage, and you can see here we are calculating the computing the address. Okay, here we compute the address, that is basically 100 plus content of R5. And then you can see what in the next stage what we are doing in the memory stage. In the memory stage, this load instruction will access the memory. Okay, and load instruction, it will read from the memory. The address has been computed by this stage. Okay, this stage will compute the address. The address is basically 100 plus content of R5. So at that address, in this stage, we will go to the main memory. At that address, the value we will bring. Okay, yes or no? So basically we are accessing the main memory. In this stage we are accessing the main memory, or I can say we are accessing the data memory. Then you can see in this write back stage, we are writing in the destination register. Okay, so you can see what is the destination register, that is register 2. So remember, in this stage we are writing in the register 2. Okay, one more thing, in the register 2 we are writing, but remember I told you that we are writing to any register in the first half of the cycle, and in the second half of the cycle we read from the register. So I can say that at this moment, I can say here we are writing to the register R2. I can say that here in the first half we are writing to register R2. Yes or no? In the first half. So you can say like this, that okay, in this first half what we are doing, we are writing to register R2. Okay, here. So let me write it here, that here what we are doing in in this in this first half of cycle 5 cycle 5. Okay, we write to register R2, or I can say that in first half of the cycle C5, R2 is written. Means at this moment we have R2 contains the value. Okay, so if some instruction need to read R2, then they can do it. Basically here. Okay, in the second half of cycle 5. In the second half of cycle 5, if some instruction need to read this R2, then they can do it. Okay, I hope you understood. This is given in the question split phase, I told you. Okay, so let's see the next. Now you can notice, what about this instruction I2? You can notice instruction I2 will go here. Okay, you can see instruction I2 we will fetch, because remember we are using a pipeline here. So you can notice that when we fetch the instruction I1, then in the next cycle I1 will go to the next stage. So what we will do, we will fetch the instruction I2. Yes or no? So we are fetching the instruction I2 from the instruction memory, and that task will be done in one cycle. Every stage is doing its task, is completing its task in one cycle. Okay, every stage is completing its task in one cycle. So you can see this instruction I2, it will go to next stage. Okay, yes or no? But notice one thing. This instruction I2, you notice I2 need to read R2 R3. Okay, you can see that this I2, you can see this instruction I1, it is writing in R2, and this instruction I2, it need to read R2. Okay, yes or no? So notice one thing, that this I2, it want to read the value of R2, and source register read, it will be done in the ID stage. So in this stage, you have to wait until R2 value you can read. Yes or no? Is this clear? Very simple point, that remember, this I2 needs to read R2. Okay. Yes or no? I2 needs to read R2 in ID stage. Okay. But you can notice that you can notice that R2 value, actually R2 value will be available after the first half of cycle 5. At this moment, R2 value actually will be available, and there is no data forwarding. There is no data forwarding, remember. So remember, because there is no data forwarding, so if this instruction I2 need to read this R2, then it will read this value when this R2, when this value in R2 will be available at this point. Okay, I hope you understood. Okay, because this instruction I2 need to read this register R2, and there is no data forwarding. So this I2 will wait to read R2. This I2 will wait until the value is available in R2 at this point. Okay, I hope you understood. So what will happen? Notice that this I2 need to wait here. I2 we need to wait here. Okay, will be in the ID stage only. I2. Why? What is the reason? Because you can see that I2 need to read R2. Okay, and you can see that after the first half of cycle 5, now here the R2 value is already available. Now I can say that in this second half, R2 value I2 can read. Okay, so basically here, notice what will happen. Here, I can say here, okay, or let me do like this, that here I2 will read, I2 reads R2, okay, here in second half of cycle C5. Okay, is this clear? Very simple. Because you can see we have a split phase. Already the question has already given to us that to any register we write in the first half of the cycle, and we can read in the second half of the cycle. So you can see that in the same cycle, you can notice this instruction I1 is writing to R2 in the first half of the cycle, and this instruction I2 is reading R2 in the second half of the cycle. Okay, so you can see that here I2 will read R2. Now this I2 was waiting to read R2. It has now read R2. So now it will go to here, EX stage. Okay, next I2, next I2. Okay, and here this I2 also will be out. Or I can say the I2 will also complete. Very simple. I hope you understood this point. So you can see this was your instruction I2. What about this instruction I3? You can see instruction I3 I will fetch here. Okay, because IF stage is available. IF stage is empty. IF stage is available. So instruction I3 I can fetch here. But remember, because this instruction ID stage, I can say the next stage is not available. Because the next stage is not available, so I3 will remain here. Okay, basically I3 will remain here. So that is the reason, because I3 has to wait here. So I'm writing like this. What it actually means, it means that I3 is continuing here. I3 is here, I3 is here. Okay. Already, please understand one thing, that this stage will do its work in one cycle. So the instruction fetch we have already completed. Instruction I3 we want to fetch from the instruction memory. That task has been completed. But the next stage is not available. The next stage, ID stage, is occupied by the instruction I2. So instruction I3 has to wait in this IF stage. Okay, is this clear? So very simple point. Here, this instruction I3 will be here. Now here you can see that this ID stage is now available. ID stage is now vacant. So I can say that now I3 will go here. Okay, let's see what this I3 has to read. Because remember, in this stage, in the ID stage, we need to read the source register also. In the ID stage, we decode the instruction and we read the source registers. Okay, so let's see what this I3 has to do. I3 will read R2 comma R1. Okay, so it is like this, that I3, what it will do? I3 will read R2 comma R1. Okay, and you can see that this I2 was writing in R1. Okay, so again you can see there is this dependency is there. Okay, so now you can see this I3 want to read R1 comma R2. I3 want to read, you can see this I3 want to read R1 comma R2. Okay, but remember this R2 is available. Okay, yes or no? I can say R2 we can read here because R2 is actually available here only. At this moment R2 is available. At this moment R2 is available. But where R1 will be available? R1 will be available where? You can see I2. I2 is writing in R1. I2 is writing in R1 and writing in the destination register, that will be done in the write back stage. So you can see that in this write back stage, this I2 will write in R1 in the first half of the cycle. Okay, yes or no? So here your R1 will be available. I hope you understood at this moment. So again, you can see that this I3 has to wait in the decode stage. Why? What are the reason? Because in this stage we read the source register. Please understand. In this ID stage, we read the source register. And the source register for I3, for this instruction 3, the source register is basically R1 comma R2. R2 is already available. I3 is not waiting for R2 because that is already available R2 value. But I3 is waiting for R1 value because R1 value will be available after the first half of the cycle. Yes or no? Okay, at this moment. So you can see that now what this I3 will do? This I3 will read this instruction 3. Instruction 3 will read this R1 here. Okay, here R1 it will read. Now that's it. So now this I3 has read R1 comma R2. So it will go to the next stage. Okay, I3, then I3, then I3, like this. Okay, here I3 will also complete. Very simple. I hope you understood. Now let's see the I4. What about the instruction I4? Here you can see that here instruction fetch stage is available. So instruction I4 we will fetch. I4 we are fetching. But remember the next stage, ID stage is not available, that is occupied. So we need to stay here. I4. Instruction I4 need to wait here. Now instruction I4 is waiting here. Then now you can see that this ID stage, next stage is available. So I4 will go here. Okay, now I4 is here. Now let's look at this I4. What this I4 is doing? I4 is your store instruction. So there is no destination register, but there are source registers. Okay, there are source registers. We are writing in the memory, but what are the source registers? What we are reading? We are reading R2 also. We are reading R1 also. Okay, we are reading R1 comma R2. Basically, I4 instruction 4 need to read R1 R2. Okay, so you can see this I4 in this stage will read the source register R1 R2. But R1 R2 both are available. Yes or no? One more thing you can see this instruction I3 was writing to R3. So instruction I3 does not create any problem. Instruction I3, it is writing to R3. But I4 need to read R1 R2. So I3 is not creating any problem for I4. I4 is actually dependent on I2 and I1. Yes or no? Because I4 need to read R1 R2. I1 I2 they are writing to R1 R2. But you can see that R1 R2 value here, R2 value available, here R1 value available. So you can see that Here I4 will read R1, R2 both. Okay, so I4 will go here, I4 will go here, I4 will go here, and here I4 will also complete. Okay, very simple. Now let's see I5. Here instruction fetch stage that is available. So I5 we will fetch. Here this stage, next stage is available. So I5 will go here. Now what this I5 need to do? I5 is basically reading R3, yes or no? Reading R3 and writing in R2. Reading R3, writing in R2. So you can see that because it is reading R3, and you can see I4 will not create any problem for I5 because I4 is not writing in any register. So I4 does not create any problem for I5. But I3 is writing in R3 and I5 need to read R3. So let's see when this R3 will be available. Means this I3, when it will write to R3. Let's see this I3 when it will write to R3. So you can see this I3 will write to R3 in the write back stage. Yes or no? In the destination register, if you want to write, then you will do that in the write back stage. Basically, here R3 will be available. Okay, notice here R3 will be available. This I3 instruction will write in the destination register R3 in the write back stage. Okay, so you can see in the first half we will write in the R3 register. Okay, very simple. So now you can see that this I5 is in the decode stage, and in this decode stage, or I can say in this stage, in this ID stage, we need to read the source register also. I5 need to read R3. So R3 we want to read, this I5 want to read R3, so it has to wait here. Yes or no? In the decode stage, in this ID stage, is it has to wait because in this stage you need to read the source register, and this R3 value will be available actually here. So you can see that at this moment, okay, here in the second half of this cycle, this I5 will read R3. Okay, now you can see that I5 will go here, I5 will go here, then I5 will go here, here I5 will complete. Okay, very simple. Now let's see the next, that is I6. I6 is here. The next stage is occupied by I5, so it will wait here. Now here I6 will go here. Now let's see what I6 is reading, what it is writing. So I6, you can see I6 is actually reading R2, R4, okay, and writing to R2. But notice one thing. Notice one thing. This R2 actually I5 is writing and this I6 is reading. Yes or no? This register R2, I5 is writing and this I6 need to read it. So I6 need to read R2 and the source register read will be done in the ID stage. So this I6 has to wait in the ID stage until this I5 will write this R2 value. I5 will write in this R2, which is the destination register. So writing in the destination register will be done in the write back stage. So let's see this I5 where it will write in R2. Okay, so you can see this I5 will write R2 here. Here R2 will be available. Here R2 will be available. I hope you understood. Okay, so you can see that I6 has to wait. I6 has to wait because I6 want to read R2. Okay, I6 want to read R2. So you can see I6 is waiting. Now here I6 will read the source register. Here I6 will read, and then you can see I6 will go, then I6 will go, then I6 will go like this. Okay, I hope you understood. So total how many cycles will be there? Let's see. You can see 1, 2, 3, 4, cycle 6, cycle 7. Then this is cycle 8, cycle 9, cycle 10, 11, 12, 13, 14. Then you can see there is 15 here, then there is 16 here, and there is 17 here. So it's like 15, 16, 17. Okay. Very simple. So that's it. Finally, I can say that 17 cycles it will take. Okay, the answer will be 17. I hope you understood. So, how many clock cycles are required for the execution of this code? The answer will be 17. So, this is the complete analysis of this question. Of course, I have taken time to explain each and every word in this question, each and every word, each instruction, okay, each step, basically step by step, what is happening, okay, why it is happening, okay, everything we have seen. I hope you understood. So, the answer will be 17. Please share your feedback for the complete analysis of this question also. Let me know, did you understand something new maybe? Okay, or was it like revision of pipeline? Okay, a lot of concepts we have revised through this question. So let me know your feedback about this complete analysis of this question also. Okay, let's solve this question from cache memory in COA subject, computer organization and architecture. So let's solve it. Consider a cache memory with 64 byte lines. So this is the line size. Four way set associative cache, 4096 sets. So this is the number of set. For a machine with 40-bit physical addresses, you have a machine with 40-bit physical address, main memory address has 40 bits. Among all the physical blocks in the system, means in the main memory, among all the blocks in the main memory, how many will be candidates for caching in a given set? For a particular set, for a particular set, how many main memory blocks are candidates for caching in that given set? Means in that particular set, how many main memory blocks can possibly map to? Okay, very simple. I hope you understood the question. Now let's solve it. So this question actually we can solve by two methods. The first method is very easy and the second method will provide you more intuition about the tag bits. Okay, so let's see the method number one. This is actually very easy. You can see we have a cache memory with 64 byte lines. Means the line size, or I can say the block size, this is a 64 byte. Block size, line size, these are basically same. Okay, so you can see 64 byte, this is the block size. Next, we have four-way set associative cache. You can see four ways. So basically we have four-way set associative cache. The number of set that is given to you in the cache memory, how many set we have? The number of set, that is 4096, these many sets we have. Okay, next, you can see that physical address is 40-bit. So tell me, in main memory, how many, what is the size of main memory? I can ask you, like here you can see that main memory address, that is 40 bits. Okay, and remember, by default main memory is byte addressable. So I can ask you, what is the size of main memory from here? What will be the size of main memory? You can see size of main memory, that will be 2 power 40 bytes. By default main memory is byte addressable, so at every address you will find 1 byte. So if you have 40-bit address, then I can ask how many locations are there in the main memory. The number of locations will be 2 power 40, and because by default main memory is byte addressable, so at every location there will be 1 byte, or I can say that every byte of the main memory has an address. Okay, so this is the meaning of byte addressable main memory, that in the main memory every byte has an address. Okay, so you can see that this is the size of main memory, 2 power 40 bytes. So let's find how many blocks are there in the main memory. What is the number of blocks in main memory? Why I am finding the number of blocks in the main memory? Because you can read the question. The question is saying that among all the physical blocks in the system, so first you find how many physical blocks are there in the system. Physical blocks simply means in the main memory how many blocks are there. Okay, so how many blocks are there in the main memory? What that will be? You can see the main memory size. This is 2 power 40 bytes. Okay, divided by the block size is 64 byte. Okay, yes or no? So what this value will be? You can see your main memory, it is 2 power 40 bytes, and Now in the main memory, how many blocks are there? How many blocks are there in the main memory? Okay, so you can see that the block size is 64 byte. So 2 power 40 divided by 64, that is 2 power 40 divided by 2 power 6. So that will be 2 power 32. Okay, yeah, sorry, 2 power 40 divided by 2 power 6. So that will be 2 power 40, 2 power 34. Okay, so it will be, so the number of blocks in the main memory, that will be 2 power 34. Very simple. Now let's see what the question is asking. The question is saying that how many will be candidates for caching in a given set? See, for a particular set, how many main memory blocks can possibly cache in that set? Okay, and it is actually very simple. Notice, in the main memory, you have many blocks. For example, let's assume this is block number 0, this is block number 1, and so on. And this is the block number. This is the block number 2 power 34 minus 1. Okay, because from 0 to this. Okay, so you can see the number of blocks in the main memory, that is 2 power 34. Okay, and the question is saying that in the cache memory we have set. Okay, we have set associative cache. So let's assume this is set 0. Okay, we will start the numbering from 0. Okay, the block numbering is also starting from 0, and the set numbering is also starting from 0, set 0, set 1, and so on. Finally we have set, you can see the number of set, that is 4096. So it will be 4095. Okay, from 0 to 4095, that is total 4096, these many sets. Now you can notice one thing, that some of these blocks will map to this set, some of the main memory blocks will cache in this set, yes or no. So it is like this. For example, this block number 0, it will cache in the set 0. The block number 1, it will cache in the set 1, like this. You already know this. Okay, for any block number, in which set it will cache. For example, if you want to find the set number, if you want to find the set number for any given block number, see, very simple, I am saying that for where this main memory block, let's assume you have main memory block bn. Okay, this main memory block bn, this will cache in which set? This caches in set number. In which set it will cache? That is very simple. What you will do? N mod 4096. Okay, very simple. Okay, so this you already know in the set associative cache, that if main memory block number is given to you, for example here main memory block number, that is n. So if you have this block number n, then in which set it will cache? For example, this block 0, it will cache in set 0. Block 1 will cache in set 1. Remember one thing, whenever this block 1 you will put in the cache memory, it will always go in the set 1. This block 1 can never go to set 0. This block 1 can never go to set 2. It will always go to set 1. This block 0 will always go to set 0. Okay, so this is the meaning of caching, I can say. Caching in. Okay, yes or no? Caching in. So very simple point, that for any main memory block bn, if the block number is given to you in the decimal, okay, so you can see for any main memory block number bn, to which set it will cache to? You can see it will cache in set number n mod 4096. Very simple. Now you can notice that for any set, if you see how many main memory blocks can possibly map to this set, how many main memory blocks can possibly map to this set, how many main memory blocks can possibly map to this set, so that will be equal. Okay, yes or no? That will be equal, because here this mod 4096, this is what we are using. Okay, yes or no? So finally I can say that for any set, if you find, for any particular set, if you find how many main memory blocks will cache, how many main memory blocks can possibly map to that set, that will be equal, for all the set. Okay, the number of main memory blocks, that can possibly map to a set, the number of main memory blocks that will cache in a set, this number will be same for all the set. Okay, so for any particular set you can find. Okay, so you can easily see for any particular set what that number will be. That is very simple. If I want to find how many main memory blocks will map to set 0, how many main memory blocks will map to set 0, then what that will be? Very simple, that will be how many main memory blocks we have. This is 2 power 34. These many main memory blocks we have divided by how many set we have, that is 4096. Okay, what you got here? You can see we have 2 power 34 divided by, this is 2 power 12. Okay, so finally what you got? You got 2 power 22. So that's it. You can see this is your number of main memory blocks that will cache in a particular set. Okay, whatever particular set you take, means these many 2 power 22, these many main memory blocks will map to set 1, these many main memory blocks will map to set 0. For any set, these many main memory blocks are the candidates for that set. For any set, these many main memory blocks can possibly map to that set. Okay, very simple. So the answer will be 2 power 22. So for this question, the answer will be 2 power 22, and this will be 4 million. Okay, of course, you can calculate it with the help of calculator. Okay, what will be 2 power 22? In the calculator, you can put 2 power 22 and you can calculate the value. That will be your answer. I hope you understood. So this is your method number 1 to solve this question. But let me tell you, there is another method. We can solve this question using another method, that is, if you have intuitive understanding of tag, what tag actually means. I have seen many students, they don't really understand the tag. What they will do, they will find the tag bits like this, that you have this main memory address. First they will find the block offset bits, how many bits are required for block offset. Then they will find how many bits are required for index. Then the remaining bits will be the tag bits. Yes or no? But you should ask yourself that this block offset you understand. Within a block, how many bytes we have? If I want to address one of those bytes within a block, if I want to identify a byte, then how many bits I need to identify this byte within a block? That is your block offset bits. Okay, that is your block offset. So this you understand. You also understand the set index, or I can say the line index. When you have direct mapped cache, then the index will be line index. And when you have set associative cache, then the index will be set index. And when you have fully associative cache, then there is no such thing as index. Okay, in the fully associative cache, we don't have index bits. So you can see basically the index also you understand. Okay, in the set associative cache, we index means set index, so that you can easily understand that how many set you have. From that you can find set index bits. In the direct mapped cache, index means line index, so how many lines we have in the cache memory, from that you can find the bits, from that you can find the line index bits needed for line index. Yes or no? But you can see, when you are finding the number of tag bits, then what you are doing, you are not using any logic. Did you ever think about it? You are using the logic for block offset bits, you are using the logic for index bits also. Here you are using the logic, here you are using the logic. Means you understand block offset, you understand index, these things actually you understand. But when you find the tag bits, then what you are doing, from total you are minusing this. Okay, you are subtracting this and you are getting the tag bits and you are very happy. You are not thinking that what is the intuitive meaning of tag. Have you ever thought about it? What is the intuitive meaning of tag? Like the way we find block offset bits, using some logic we are finding the block offset bits. See, how do we find the block offset bits? Very easy. What you will do, you will see the block size. If the block size is 2 power n bytes, then you can easily see that the block offset bits, that will be n bits. Okay, very simple. Also for index, you can see, let's assume we have set associative cache, and in the set associative cache, let's assume we have 2 power k set. then in that case I can say set index bits, that will be k bits. Okay, so you are using a logic, but to find the number of tag bits you are not using any logic like this. You are just subtracting from this total number of bits in the address, you are subtracting these many bits and you are getting the number of tag bits. So now let me tell you, actually in go classes cache memory lectures, in go classes coa lectures, everything we have understood with intuition. Okay, everything, all these things we have already seen. We have also seen the intuitive meaning of tag. Okay, how to find tag without going through like this. Of course this is the easy way. Okay, first you find these many, okay, first you find these bits, then from the total number of bits in the address you remove these bits, that will give you the number of tag bits. This is the easy way. But what is the intuitive idea, what this tag actually means, the number of tag bits, what they identify, okay, from where they are coming? So this is your intuitive understanding of tag. Let me explain this. You can see under this question, this is our all India mock test question, where I am asking that among all the physical blocks in the system, how many will be candidates for caching in a given set? In the main memory, there are main memory blocks. Out of them, how many will be candidates for caching in a particular set? And you can see this comment I made. I made this comment that this question is basically asking for number of tag bits in the physical address. And there are many comments. Some students are asking, sir, how do you know from this question? How do you know that this question is related to tag bits? Okay, this question is actually related to tag bits, but how do I know that this question is related to tag bits? The reason is because I understand the intuitive way of tag. I understand the intuitive meaning of tag. What is the intuitive meaning of tag? If you understand that, then of course this type of questions you can very easily solve. Already one method we have already seen to solve this question, one method we have already seen, but let me show you another method also. Maybe that will give you some better understanding about the tag. Okay, the intuitive understanding of tag. So let's see intuitive understanding of tag. Let me quickly tell you. You can see each cache line has an associated tag. This we already know. We basically cache memory has two parts, one is data array, another is tag array. Okay, in the data array we have lines, okay, cache lines, and corresponding to every cache line in the tag array we store a tag. Okay, remember in the data array we have data array, we have tag array. Cache memory has two parts. In the data array we have lines. Corresponding to every line in the tag array we store a tag. Okay, so you can see here that every cache line has an associated tag. And what this tag will identify? This tag will actually identify which particular memory block is currently being stored in that line. Okay, I will explain it, don't worry. But the point is, this is the intuitive meaning of tag. This tag, remember, for any line, for any cache line, there is an associated tag, and this tag will identify which particular memory block is currently stored in that line. Okay, so you can see that tag or tag bits of a cache line, they will identify the block that is stored in that cache line. Let me explain this with some example. So let me take direct mapped cache. I will take all the examples. So first let's consider direct mapped cache. In this direct mapped cache, let's assume there are four cache lines. Okay, let's quickly see. Let's assume there are four cache lines. So you can see this is line 0, line 1, line 2, line 3. Okay, so these are the four cache lines. And let's assume in the main memory there are 16 blocks. In the main memory, these are the block numbers. Block 0, block 1. Okay, this is block 15. So these are the block numbers, and this is your main memory, and this is your cache. Now you can see this is a direct mapped cache. So you can notice this block 0 will map to line 0, block 1 will map to line 1, block 2 will map to line 2, then this block 4 will map to line 0. Okay, so like that, you already know this. Okay, so you can see. Now you tell me how many blocks, how many main memory blocks can possibly map to line 0? So you can see that in this line 0, which main memory blocks will cache? Means I can say that B0, B4, B8, B12. Yes or no? These main memory blocks, these are the candidates for line 0. Correct? Do you agree with me? Okay. In the main memory, these blocks, only these blocks can go to line 0. No other block can go to line 0, remember. And remember, these blocks, they will never go to line 1. They will never go to line 2. These blocks will only go to line 0, and only these blocks can go to line 0. No other block can go to line 0. So basically, I can say that for this line 0, these are the candidates. These main memory blocks are the candidates. Okay, so you can see that for this line 1, these main memory blocks are the candidates B1, B5, B9, B13. Okay, like this, you already know. There are 4 main memory blocks which are candidates for line 2, and there are 4 main memory blocks which are candidates for line 3. So basically, for every line, what is the number of candidates? What is the number of candidate main memory blocks? That is basically 4. So remember one thing. Think from the line point of view. Every line has an associated tag. These lines, these are basically part of data array, and corresponding to every line in the tag array, we store a tag. So you can see, corresponding to every line, there is an associated tag. Now you can notice that for this line 0, these are the candidate main memory blocks. Means only these main memory blocks can map to line 0. No other main memory block can map to line 0. Okay. Of course, at a time, one of them will be here. Okay. It cannot happen that at the same time both are in this line, because line size is equal to block size. So at a time, more than one cannot be present in a line. But I'm saying that these are the candidates for line 0. It means at different times, these blocks you can find in this line 0, but no other main memory block can ever be present in the line 0. So that is the reason I am saying that these are the candidates for line 0. Now you notice that from the line 0 point of view, we just need to identify one of them. Okay, think from the line 0 point of view. Let's assume you are line 0. Now, from the line 0 point of view, we just need to identify one of them. One of these 4. We don't need to identify one of these 16. In the main memory, we have 16 blocks. In the main memory, there are 16 blocks. But remember, from this line point of view, we just need to identify one of these candidate blocks. Okay, and you can see, if I need to identify one of 4 blocks, these are the 4 memory blocks. These are the 4 main memory blocks which are candidates for this line 0, and I need to identify one of them. So how many bits I need to identify one of them? Only 2 bits I need. That is your tag bits. That's it. Okay, is this clear? So remember, the number of tag bits here, what that will be? The number of tag bits, what that will be? That will be 2 bits only. Okay, because you can see that for any line, if you see, what is the number of candidate main memory blocks for that line? That is 4. So from that line point of view, we just need to identify one of these candidate main memory blocks. And if I want to identify one of these 4 blocks, then I need only 2 bits to identify 4 blocks. Using 2 bits, I can identify 4 blocks. So the number of tag bits, that will be 2 bits. So this is what I was saying. I was telling you that the tag bits or tag of a cache line, for every cache line, there is an associated tag. And you can see what this tag will identify. This tag of a cache line will identify the block stored in that cache line. Or I can say that this tag of a cache line, it will identify the candidate main memory block for that cache line. Okay, is this clear? Very simple. I hope you understood. So you can see in this situation, for this situation, I can say for this particular cache memory, for this system, I can say that number of tag bits, that actually will be 2 bits. Let's consider set associative cache also. Let's take a cache with 4 lines. We have a cache with 4 lines, but two-way set associative. So every set has 2 lines. So basically you have 2 set 0, set 1. Okay, total we have 4 lines, but remember we have 2 set 0, set 1. Okay, this is two-way set associative cache. Now let's again take the same example. Means our main memory has 16 blocks. Block 0, block 1, block 2, block 3, and so on. Block 15. Okay, again you can see this is the main memory and this is the cache memory. Okay, now you can again notice that this block 0, it will always map to set 0. Block 1 will map to set 1. Block 2 will map to set 0. Block 3 will map to set 1. Yes or no? Okay, so you can see one more thing. Notice one more thing. Think from the line point of view. See, block 0 will always map to set 0. Block 0 can never map to set 1. So block 0 will always map to set 0. But in the set 0, the block 0 can go to this line or can go to this line. So remember, from this line point of view, block 0 is a candidate. Okay, also notice this block B2, this will always go to set 0. Block B2 can never go to set 1. So block B2 will always go to set 0. But in this set 0, this block B2 can go to this line or to this line. So from this line point of view, this block B2 is also a candidate. Okay, so tell me, all the candidates for this set, these are the candidates for this line also, these are the candidates for this line also, yes or no? So basically all the candidates for a particular set, all the candidate main memory blocks for a particular set, these are candidate main memory blocks for every line in this set also. Okay, so you can see that, I can say that what are the candidates for this set 0, or I can say for every line in this set 0, what are the candidate main memory blocks? You can see these are B0, then B2, then B4, and so on. B14. Okay, yes or no? Total how many? Total 8. Okay, and these are the candidate. These are the candidate blocks for set 0. Okay, is this clear? These are the candidate blocks for set 0. Candidate main memory blocks for set 0. Okay, candidate main memory blocks for set 0. I hope you understood. Okay, so you can see. Similarly, remember how many candidate main memory blocks for set 1? There are 8 candidate main memory blocks for set 1 also. Okay, yes or no? Very simple point that there are 8 candidate main memory blocks for set 1. There are 8 candidate main memory blocks for set 0. And also notice one thing. For this line, we have 8 candidate main memory blocks. For this line, we have 8 candidate main memory blocks. For this line, we have 8 candidate main memory blocks. For this line also, we have 8 candidate main memory blocks. Because remember, tag bits are associated with every line, not with every set. Okay, if you have set associative cache, it does not mean that with every set we have a tag associated. No, tag is associated with every cache line. Whatever type of cache memory you take, fully associative, direct mapped, set associative, whatever type of cache memory you take, remember tag is associated, tag corresponds to line. Tag is associated with every cache line. So if you have set associative cache, don't say that with every set tag is associated. No, tag is always associated with cache line. So you can see that here, you can see that for this cache line we have 4 candidate main memory blocks. For every cache line we have for this cache. So notice one thing, for this cache line we have 8 candidate main memory blocks. For this cache line we have 8 candidate main memory blocks. For every cache line we have 8 candidate main memory blocks. Okay, yes or no? So here I can say that every cache line has 8 candidate main memory blocks. Every cache line has 8 candidate main memory blocks. If every cache line has 8 candidate main memory blocks, then remember, think from that line point of view. Let's assume you are that line. Okay, let's assume you are that line. Then remember, you just need to identify one of these 8 blocks. So how many bits you need to identify one of 8 blocks? 3 bits only. Yes or no? 3 bits, tag bits. So remember how many tag bits you need? So number of tag bits that I need, that will be 3 bits. Okay, is this point clear? Very simple. I hope you understood this point. So remember, think from the line point of view, think from the cache line point of view. If you are a cache line, then you just need to identify one of these 8 candidate main memory blocks, because only these blocks can come to this line. Yes or no? The remaining blocks can never come to this line. Yes or no? Okay, so from this cache line point of view, you can see that only these 8 candidate main memory blocks are there. We need to identify one of them. So we need 3 bits. That's it. I hope you understood. Very simple. Okay, this is the intuitive understanding of tag bits. Is it clear? Let's consider a set fully associative cache also. No problem. Okay, so let's take again 4 lines. This is our cache memory. We have a fully associative cache L0, L1, L2, L3. 4 lines we have. And what we have here? We have main memory with 16 blocks. Okay, again we have, let's assume 16 blocks, B0, B1, B2, and so on, B15. So the main memory has 16 blocks. Okay, now you notice, because we have fully associative cache memory, so any main memory block can cache in any line, yes or no. So notice, think from this line point of view. Let's assume you are this line. Let's assume you are this line 0. Think from this line 0 point of view. How many main memory blocks can possibly map to this line 0? All of them, yes or no? I can say that from this line point of view, I can say that all these main memory blocks are the candidate main memory blocks for line 0, yes or no? So you can see that B0, B1, and so on, B15. Basically, I can say that all the main memory blocks are the candidate main memory blocks for line 0, yes or no? Okay, so I can say that all main memory blocks are the candidates for to cache in line 0, are the candidates to cache in line 0. Okay, so you can see the same thing is true for line 1, the same thing is true for line 2, line 3, like that, yes or no? So I can say that basically all these 16 blocks, 16 candidate main memory blocks, candidate main memory blocks. Okay, so for every line, how many candidate main memory blocks are there? Tell me. You can see for every cache line has, every cache line has 16 candidate main memory blocks. Okay, because this is a fully associative cache memory, so any main memory block can map to any cache line. Okay, so here I can say that every cache line has 16 candidate main memory blocks. So what will be the number of tag bits? You can notice that, think from any line point of view, you can see that this line, look at this line L3, this has 16 candidate main memory blocks. So any of these 16 main memory blocks can be present in line 3, yes or no? So this line 3 has to identify one of these 16 people. This line 3 has to identify one of these 16 candidate main memory blocks. To identify one of these 16, how many bits I need? 4 bits, yes or no? Using 4 bits, I can identify 16 main memory blocks. Okay, yes or no? So this is the idea. I hope you understood. So number of tag bits will be 4 bits. Now, I can conclude now. Remember, whatever cache memory you take, set associative, direct mapped, fully associative, whatever cache memory you take, very simple point that for any cache line, for any cache line, for any cache line, if 2 power k candidate main memory blocks are there, for any cache line, if 2 power k candidate main memory blocks are there, okay, I can say whatever cache memory you take, whatever type of cache memory you take, then for any cache line, if there are 2 power k candidate main memory blocks, then the number of tag bits, what that will be? That will be k bits. Okay, because remember, every cache line has 2 power k candidate main memory blocks. Okay, whatever cache line you take, the number of, remember one thing, the number of candidate main memory blocks, this will be same for every cache line. Okay, so whatever cache line you consider, you can consider for every cache line the number of candidate main memory blocks that will always be same whatever cache memory you take. Okay, so you can see that for any cache line, I can say if there are 2 power k candidate main memory blocks are there, then I can say the number of tag bits that will be k bits, because we just need to identify one of these 2 power k people. And to identify one of these 2 power k people, we need k bits. Using k bits, we can identify 2 power k main memory blocks. I hope you understood. Okay, so this is the idea. And same thing I've written here. Okay, this is from the Go classes lecture notes. This slide as it is I have taken from the Go classes lecture notes. So you can see this, that for a cache line, first you find how many candidate main memory blocks are there. What is a candidate main memory block? Candidate main memory block for a line, what is that? These are those main memory blocks which can possibly map to that line. For a cache line, if there are 2 power p candidate main memory blocks, then basically we need p bits for tag. Okay, because remember, we just need to identify one of these 2 power p candidate main memory blocks for that line. We just need to identify one of these 2 power p blocks. To identify one of these 2 power p blocks, we need p bits to identify, and this is called tag bits. Okay, so we need p bits in the tag for that line. Okay, very simple. I hope you understood. Let's solve this question quickly. Assume that we have 2 power k way set associative cache, means every set has 2 power k lines. Okay, you can see we have 2 power k way set associative cache, so every set has 2 power k lines. Next, the number of cache lines 2 power l, the number of blocks in the main memory 2 power b. Now the question is asking, to a particular set, how many blocks will possibly map to a particular line, how many blocks will possibly map to, the number of bits required for tag. Notice one thing, in the set associative cache, for any particular set, how many candidate main memory blocks are there, that is same as the number of candidate main memory blocks for any line in that set. Yes or no? Because remember, let's assume this is a set, this is a particular set. In this set, if for this set let's assume you have 64 candidate main memory blocks. Then remember, these 64 main memory blocks, they can map to any line in this set. So for every cache line, I can say that we have 64 candidate main memory blocks. Yes or no? Okay, very simple point. I hope you understood. So remember that, let's see the solution. So you can see the solution now. Notice one thing, to a particular set, how many blocks can possibly map to a particular line, how many blocks can possibly map to. So these two answers definitely will be same. Yes or no? Without solving this question, I can say that this answer, whatever is this answer, okay, let's call it answer 1, and let's call this answer 2. Then one thing is guaranteed, that answer 1, answer 2, they are basically same. Okay, yes or no? Answer 1 is same as answer 2, is same as answer 2. Okay, one more thing. If your answer 1 is, let's assume for a moment, let's assume the answer 1 is 2 power y, or maybe 2 power m. Okay, let's assume this answer, of course, answer 1, answer 2, they are same, so 2 power m. Now you can notice one thing, if the answer 1, answer 2, if they are 2 power m, then you can see that for any particular line, how many main memory blocks can possibly map to that line? If that is 2 power m, then I can say that for any particular line, for any cache line, the number of candidate main memory blocks, that is 2 power m. So these one of these 2 power m blocks, one of these 2 power m main memory blocks will cache in this particular line. So from this particular line point of view, I can say that we just need to identify one of these 2 power m main memory blocks. To identify one of them, to identify one of these 2 power m people, we need only m bits. This is called tag bits. To identify one of these 2 power m candidate main memory blocks, we need m bits, and this is your tag bits, number of tag bits. So remember, what will be the number of tag bits? That will be m bits. We just need to find what is this m. Okay, so let's see this. How to find this? Very simple. You can see we have 2 power k way set associative case. So in one set, every set has 2 power k lines. Okay, and total number of lines, that also we have. Now the question is saying that we have number of blocks also we have in the main memory. So you can see, for any particular set, how many blocks can possibly map to that set. You can see this 2 power m, what this will be equal to. You can notice, first of all, what are the number of set. You find what are the number of set, that you need to find first. Okay, what will be the number of set in the set associative case? What will be the number of set? That will be equal to the number of lines divided by, in one set, how many lines you have. In one set you have 2 power k lines. Okay, so that is basically 2 power l minus k. Yes or no? Okay, this is the number of set. Now once you have this number of set, then you can see how many main memory blocks will possibly map to a particular set. So I can say that for a set, for any set, what is the number of candidate main memory blocks? What that will be? Very simple, that will be equal to the number of blocks in the main memory divided by how many sets you have. So that is basically 2 power l minus k. What this will be? This will be 2 power b minus l plus k. Okay, yes or no? So finally this is equal to 2 power b minus l plus k. Okay, so what will be the number of tag bits? The number of tag bits, this will be equal to b minus l plus k. Okay, so easily you can solve this question. I hope you understood. Very simple. So let's come back to this question. For this question, we have seen this revision, whatever we have done, the complete revision that we have done to intuitively understand the tag. Now I hope that you can say that, okay, I intuitively understand what is this tag. With every case line, we are storing a tag in the tag array. What is this tag, and what this tag indicates? How to find the number of tag bits intuitively? Okay, so I hope you understood the intuitive meaning of tag bits. Now let's solve this question. With that understanding, we can solve this question. So you can see that the question is asking that among all the physical blocks in the system, among all the physical blocks in the system, how many will be candidates for caching in a given set? Remember, in a given set, let's assume this is a given set in the cache memory. This is your cache memory. In this cache memory, let's assume this is a set. This is a particular set. Let's assume this is set 0. Any set you can take. Okay, so let's assume this is set 0. Now already the question is telling you that we have 4-way set associative cache, means there are 4 lines here. Correct, we have 4 lines here, and this is your cache memory. Okay, now you can see the question is asking that how many will be candidates for caching in a given set. See, in this given set, how many main memory blocks can cache in this given set? So what that will be equal to? Let's assume for a moment, let's assume that 2 power k blocks, main memory blocks, 2 power k main memory blocks. By default, when I say block, means main memory block. Okay, because the same thing, when it is in the main memory, it is called block. When it is in the cache memory, it is called line. Okay, very simple. So you can see that, assume 2 power k main memory blocks are candidates for set 0. Okay, assume 2 power k main memory blocks can possibly map or cache in set 0. Okay, now you can notice that in this set 0, whatever line I consider, if I consider a particular line, if I consider any particular line, then you can see that all these 2 power k main memory blocks, they can cache in this line? Yes or no? Okay, because these 2 power k main memory blocks, they will go to set 0, but in this set 0 they can go to this line, they can go to this line. So basically I can say that for this line, how many candidate main memory blocks are there? That is also 2 power k. For this line, how many candidate main memory blocks are there? That is also 2 power k. For every cache line, for every cache line in this entire cache memory, for every cache line, how many candidate main memory blocks are there? That is 2 power k. Okay, yes or no? So you can see that all the candidate main memory blocks for this set, these are also candidate main memory blocks for every line in this set. Okay, is this clear? Very simple. So you can see that if you want to identify one of them, then how many bits you need? K bits you need. So you can see the number of tag bits, that will be equal to k. That will be equal to k. The question is actually asking 2 power k. For this particular question, the answer for given question, the answer for given question, the answer for given question will be 2 power k, and the number of tag bits you can find, that will be k. Okay, so let's find the number of tag bits. For that, you have one method. What is that? How to find the number of tag bits? For that, you have this method, that this physical address you can divide. Okay, so you can see this is your physical address. Physical address. This physical address has 40 bits. Okay, so this physical address in the set associated to cache memory, this physical address I can split into 3 parts. These 3 parts are basically block offset, index means set index in the set associated to cache memory, and this is the tag. So you can see that this is your block offset. Okay, this is your index in the set associated to cache memory. Index means set index. It will identify the set. Okay, so you can see, and it is your tag. This tag will identify one of the candidate main memory blocks. Okay, so you can see candidate main memory blocks. This block offset, this will identify the byte within a block. This block offset, it identifies a byte, a particular byte within a block. Within a block. Okay. Also notice one thing, that this tag, what it will do, it identifies it identifies a, it identifies a candidate main memory block. Okay, very simple. And this set index, this identifies set number. Okay, very simple. So you can see the block size is given to you. The block size is equal to line size, that is 64 byte. So you can see that here you need 6 bits. Okay, next you can see how many set we have. 4096 set we have. So the number of set, that is 4096. So for set index we need 12 bits. So for tag, how many bits we need? For this tag, how many bits we need? That will be 40 minus 12 minus 6. What that will be? 40 minus 18. 22 bits. So number of tag bits, that will be equal to 22 bits. And this is equal to k. The question is asking 2 power k. Okay, yes or no? So you can see we got the k value. So you see that k value is actually 22 bits. So the k value we got, that is 22. And the question is asking what will be the answer? The answer will be 2 power k, that will be 2 power 22. Okay, I hope you understood. Very simple. So this is the complete analysis for this question. I hope you understood. Okay, so I hope you understood the complete analysis of each question that we have seen so far. Let me also tell you one thing. If you want to attempt all the Go classes mock test, if you want to attempt all the Go classes, all India mock test also, and all the mock test also. So let me tell you, we have total 20 mock test, including the all India mock test. Total 20 mock test, full length mock test. I am talking about full length mock test. So Go classes Gate CS test series. Go classes Gate CS test series has 20 full length mock test, including the All India mock test. Our Gate DA test series has 15 mock test, including the All India mock test. And in the combo CS plus DA combo, you will get 20 plus 15, 35 full length mock test you will get, including the All India mock test. So if you missed our previous All India mock test, and if you want to attempt our previous All India mock test, also you want to attempt all the mock test in our test series, then this full length mock test package we have launched. So you can see Go classes full length mock test package. This package we have launched. The price of this package is much cheaper than the price of test series. Okay, I think in the last 1 month most of you want to attempt the full length mock test. That is the reason this full length mock test package we have released. Okay, so you can attempt the full length mock test. And how to enroll, where to enroll? So let me tell you that you can just visit the Go classes website. On the Go classes website, you click on this button. Okay, just click on this button. Then you can see, you will see this is the full length mock test package. So you click on this full length mock test package, and there you can decide, you can choose if you want Gate CS full length mock test, Gate DA full length mock test, or CS plus DA combo full length mock test. Okay, so you can enroll, and then you can attempt all the previous All India mock test, all the future All India mock test, all the mock test which are not All India mock test, all those mock test also you can attempt. Okay, so I hope you understood. And remember, the future All India mock test, they are free for all the aspirants if you attempt live. Okay, so during the live window, you know, every Saturday we have Gate DA All India mock test. Every Sunday we have Gate CS All India mock test. And when you attempt the All India mock test in the live duration, then it is free for everyone. But if you miss it by any reason, if you miss to attempt the All India mock test in the live window, then later if you want to attempt the All India mock test, then you must enroll either in our test series, you must be enrolled in the Go classes test series, or you must be enrolled in the Go classes full length mock test package. Okay, so I hope you understood. You can check it out on the Go classes website. Let's solve this question based on regular expression from theory of computation subject. The formal definition of a regular expression over alphabet sigma, some alphabet sigma you have. The formal definition of regular expression that is given to you. We already know this formal definition actually. This is given to you that this symbol phi, this is a regular expression, and it will correspond to the empty language. You can see the symbol epsilon, this is a regular expression, and it will correspond to the language containing this epsilon. Okay, very simple. And for every symbol in the alphabet, means for every input alphabet symbol, so you can see for every symbol in the alphabet, that symbol is also regular expression. If R1, R2 are regular expression, then R1 union R2 is also a regular expression. If R1, R2 are regular expression, then their concatenation is also a regular expression. If R is a regular expression, then R star is also a regular expression. So this is the regular expression formal definition given to us. Now the question is asking, for a regular expression E, let LE be the language generated by E. You already know that every regular expression will generate a regular language. For every regular language, there is a regular expression. So for a regular expression E, let's assume LE, this is the language generated by E. If E is a regular expression that has no clean star in it, this star means clean star. So if you have a regular expression that has no clean star occurring in it, then what can you say about this E? What is true about this E? So the options are given to you. You can read them. The options are saying that LE is empty, LE is finite, complement of LE is empty. Both LE comma its complement are infinite. Okay, so let's solve this question. You can see the question is saying that we have a regular expression that does not contain any clean star. If your regular expression does not contain any clean star, And also remember, in this definition, you can see we don't have clean plus. Please notice that is the reason this definition is given to you. I've seen many students, what they are doing, they are asking, sir, if the regular expression does not have clean star, then maybe it can have clean plus. But remember, that is the reason this definition is given to you. This definition is already saying that in this definition, you can notice that there is no clean plus. Okay, that is the reason I gave you this definition. Otherwise, why would I increase the paragraph? Okay, yes or no? So very simple point. I knew before making this question, I knew that many students will come to me and they will ask me, sir, if the regular expression does not have clean star, then maybe it can have clean plus, because using the clean plus also we can create infinite language. I knew this type of doubt will come. That is the reason I gave you this formal definition of regular expression. But even after giving this formal definition of regular expression, which does not contain clean plus, this given definition does not contain clean plus, still many students have made this silly mistake. They are asking, sir, why we cannot consider clean plus? The reason is because it is not given in the formal definition given in the question. You have to understand the definition given in the question and then you have to solve the question. Very simple. So now remember, if your regular expression does not contain clean star, then definitely the language will be finite. You cannot generate infinite language. Of course, you can formally prove it. See, look at all the rules. You can see, look at all the rules for regular expression. Look at the first rule. The first rule is saying that this phi is a regular expression. If this phi is a regular expression, then what will be the language? Okay, on one side, I am writing the regular expression. On one side, I'm writing the language. Now you can see that the the rule number one is saying that phi is a regular expression. And this phi regular expression, this corresponds to which language? This corresponds to empty language. Empty language is also a finite language. Yes or no? This is also a finite language. Next, you can see, look at the next rule, that is the symbol epsilon. This is a regular expression. This symbol epsilon, this is a regular expression. Now you can see that this epsilon, this corresponds to which language? This corresponds to set containing epsilon, this language. Again, this is a finite language. Yes or no? Let's look at the rule number 3. For every alphabet symbol, that alphabet symbol is also a regular expression. Okay, for example, let's assume this A. This is a alphabet symbol. Okay, this A belongs to sigma. This A belongs to sigma. So you can see that this A is also a regular expression. This A corresponds to which language? This corresponds to set containing A language. This is also finite language. Okay. Now look at the next rule. The next rule, you can see that if R1, R2 are regular expression, then their union is also a regular expression. Okay. Now notice, I am saying that if R1, R2 are regular expression, then their union is also a regular expression. Now, so far from all these previous rules, you can notice that so far all these previous rules, they are generating finite language. So union of finite language, that is also finite language. Yes or no? You already know this, that finite language, union finite language, that will be what? That will be a finite language. Correct? Very simple. Now let's see the rule number 5. The rule number 5 is, if R1, R2 are regular expression, then their concatenation is also a regular expression. So you can see R1 concatenation R2, this is also a regular expression. Look at the previous rules. All the previous rules you look at, from 1 to 4, all the rules you look at, you can see that they are generating finite language, all these previous rules. So what are the concatenation of finite language with finite language? Finite language, concatenation with finite language. So the concatenation of two finite languages, that also will be a finite language. Okay, very simple. So can you notice that these 5 rules, they are only creating the finite language, nothing else. Using these 5 rules, we can only generate regular expression which will correspond to a finite language. Yes or no? Using these 5 rules, we can generate only those regular expressions which will correspond to a finite language if we do not use the sixth rule. If we do not use the rule number 6. Because remember, the question is saying that this regular expression E does not contain clean star. So do not use the rule number 6. Do not use it. Don't use this rule number 6. Accept this rule number 6. If I don't use this rule number 6, then you can notice that using these rules, rule 1 to 5, using these rules, we can generate only those regular expressions which will generate only finite languages. This is the proof. So you can see the answer will be that LE is finite. I hope you understood. Remember, option A, LE is empty. This is not necessary. For example, I can give you, consider this regular expression. Let me give you a regular expression, for example, AB or AAA. Okay, so you can see, consider this regular expression. AB union. Okay, here we are using this union AAA. Okay, so now you can see that this is a regular expression that does not contain clean star. There is no clean star. But if you look at the language, if you look at the language generated by E, then that is basically AB comma AA. So this is not empty. Next, you can see complement of LE will be empty. The complement of this language is also not empty. So this is also eliminated. Both LE comma its complement are infinite. LE is actually finite. Yes or no? Yes, complement will be infinite because the complement of finite language will be infinite. But LE is actually finite. So this option is also gone. So for this question, the answer will be option B. I hope you understood. Very simple question. Let's solve this question. Considering A and B as two logical variables, A comma B, these are two logical variables. So they can take true or false, or you can consider them Boolean variables. Okay, next, the expression not of A and B or A and not of B, this is true for what? So you can see that this expression is given to you. First, let me tell you what this expression is. You can see there is a or here. There is a or here. Then what we have here and what we have here. Let's see. So you can see we have not of A, negation of A and B, negation of A and B. What we have here, A and negation of B. Okay, so this is the expression. You can see this is the expression A bar B or AB bar. Remember, this is a standard expression for exclusive or XOR. Yes or no? So this is actually XOR of A comma B. And we already know when this XOR will be 1, you can see this XOR will be 1. This is exclusive OR. So you can see this XOR will be 1 when both A comma B are different. And when both A comma B are same, then XOR will be 0. Okay, so the answer will be what? You can see this expression will be 1. This expression is true whenever A is different from B. So for this question, the answer will be option C. I hope you understood. Look at the option A. For all values of A comma B, no. If you take A, B equal to 1, 1, then this expression will be 0, or I can say this expression will be false. This is the truth table of A XOR B. Let me make the truth table of A XOR B. You can see this is A, B. So you can see false, 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 true, true, false, true, true. So you can see this XOR, this is true when A comma B are different. Okay, so you can see here it will be true, true, and here it will be false, here it will be false. So you can see that. Look at option A. This expression is true for all values of A comma B. No. This expression is true whenever A is equal to B. No. Whenever A is equal to B, then this expression is actually false. Okay, yes or no? This expression is true whenever A is false. No. You can see here A is false, but this expression can be true or false depending on B. So you can see this is also not correct. So for this question, the answer will be option C. I hope you understood. Very simple question. Let's solve this question. Consider a logic circuit with 3 inputs A and B and C and one output S. Considering the output value S is equal to the input value A when input B and C are at the same logic level. Means when B comma C are equal, then this output will be same as A. Next, You can see the output value S is equal to inverse of input value A when input B and C are opposite logic levels. Means when B comma C are different, then output S will be equal to A complement. Select the alternative that presents the logical expression corresponding to the circuit. Means basically the expression for output S. The best way to solve this question, that is option elimination. Okay, very easily you can solve this question. First, you understand what information is given to you. This is a very easy question from the digital logic. So you can see the question is saying that we have a logical circuit. There is a logical circuit, and for this logical circuit, we have three inputs A, B, C, and there is one output, that is S. The question is saying that when input B comma C are equal, means they are at the same logic level, means both are 0 or both are 1. So means when B comma C are equal, then S equal to A. So it is given to you basically that when B equal to C, then S must be equal to A. Okay, and remember, when B is not equal to C, then S must be equal to A complement. Okay, you can see that S is equal to A when B comma C are same. And you can see S is equal to A complement when B comma C are opposite, means they are different. Okay, now we need to write the expression for S. So from the options, we can very easily eliminate the options. Okay, using this information, you can see when B and C, when they are equal, then remember we should get S equal to A. So let's check let's check option A. Okay, already we know this point that when when B equal to C, okay, when B equal to C, then remember what we should get, we must get S equal to A. Okay, we must get S equal to A. So let's see option A. You can see when B equal to C, then what it will become, it will become 0. Yes or no? So we are taking the case, remember we are taking the case 1. We are taking the case 1 when B equal to C. Okay, so just consider when B equal to C, what is the desired answer, what is the desired S, that will be A. Okay, when B equal to C, then S will be equal to A. So let's see option A. In the option A, you can notice we have A and B XOR C. So you can see that when B comma C are same, then what will be their XOR? When B comma C are same, then what will be their XOR? B XOR C, that will be 0. Okay, and you can see this will be 0. And finally, what is A and 0? That will be 0. So you can see that S is equal to 0. But what we want S to be equal to A. We are not getting S equal to A. Okay, so option A is gone. Option A eliminated. Very simple. Next, you can see, what about option B? Remember, XOR is commutative and associative. So you can calculate this first. Okay, because XOR is commutative and associative. So what is this B XOR C? This will be 0 because B equal to C. B equal to C means B XOR C, that will be 0. What is A XOR 0? What is, you can see A XOR 0. Okay, remember one thing, you already know this, that A XOR B, that is equal to A bar B or AB bar. Okay, so what will be A XOR 0? What that will be? That will be A bar 0 or A 0 bar. Okay, so you can see this will be 0, this will be 0, and it will be A. So remember what we got? We got A. A XOR 0, that is equal to A. So finally here we got A. This is what we desire. So means option B is not eliminated. What about option C? In option C, you can see this B XOR C, this will become 0. What is A bar XOR 0? That will be A bar. Yes or no? Already we have seen this, that alpha XOR 0, that will be alpha. Okay, there is another way to prove it. See, either you can use this formula, or what you can do, notice alpha XOR 0. What should I write here? Okay, this is very simple. This is actually fixed. This 0 is actually fixed. So you just focus on this alpha. Notice if this alpha is 0, then what is 0 XOR 0? That will be 0. So you can see the result will be 0. If alpha is 1, then what is 1 XOR 0? That will be 1. So you can notice that This is same as alpha. Yes or no? So it means that here I should write alpha. So alpha XOR 0, that will be equal to alpha. So here you can see that in this option C, what we got? In this option C, we got S equal to A bar. So option C is also gone. Okay, yes or no? Now let's see option D. In option D, what we have? You can see B XOR C, then complement. Okay, so here what you got? B XOR C, that is 0, because we are considering case 1 when B equal to C. So when B equal to C, then B XOR C, that will be 0. The complement of 0, that will be 1. So now we have A XOR 1. Now let's see what is A XOR 1. A XOR 1. You can apply this formula A bar 1 or A1 bar. Okay, yes or no? So here what you got? You got A bar. Okay, very simple. So I can say that alpha XOR 1, that actually will be alpha bar. There is another way to show it. You can see alpha XOR 1, what that will be. What this will be. What should I write here? Very easy, remember. You can see this 1 is fixed. Okay, this is actually fixed. So I can say that if this alpha is 0, then what is 0 XOR 1? That will be 1. If alpha is 1, then what is 1 XOR 1? That will be 0. Did you notice that you are getting opposite? If alpha is 0, output is 1. If alpha is 1, output is 0. Means here what should I write? Here should I write alpha complement. Okay, very simple. So here you can see in this question, look at option D. In the option D, we have A XOR 1, so that will be A bar. But what is desired? What is desired? Desired is S should be equal to A. So this option is also gone. 3 options gone, so definitely option B will be correct. Okay, is this clear? Very simple. You can also focus on this option B. Let's focus on this option B. You can easily notice this is what we want from this circuit. From the behavior of this circuit, you can see that when B equal to C, then S should be equal to A. And when B is not equal to C, then S should be equal to A bar. This is what we want. You can actually focus here that if B equal to C and if B is not equal to C, okay, C. If B equal to C, then this B XOR C, this will become 0. So here A, this S will become A XOR 0 and that will be A. And you can see when B is not equal to C, then this XOR will become 1. Then I will get S equal to A XOR 1 and that will be A bar. This is what we want. Okay, yes or no? This is the behavior of the logic circuit and this is the behavior of option B. So definitely option B is the correct answer. I hope you understood. Very simple. So that is enough for this session. I hope you loved this session. We have done the complete analysis of all the questions that we have seen in this session, and the remaining questions I will discuss in the next session. Okay, so let me tell you, this is the GATE-CS All India mock test schedule by goclasses. Every Sunday we have GATE-CS All India mock test. Okay, and every Saturday we have GATE-DA All India mock test. Okay, so Saturday GATE-DA All India mock test every Saturday. Every Sunday GATE-CS All India mock test. So don't miss it. Okay, thank you everyone. Please share your feedback in the comments. Let me know for which question the complete analysis did you love the most. Please share your feedback. Just put one comment, that will help us. Okay, and in the next session I will provide the complete analysis of the remaining questions also. Okay, thank you everyone.